weeks ago.
The fact that it was a failed attempt at baking biscuits. Somebody said, "Oh, this is a death bomb," and the name stuck.
By the way, Sarah, you DM'd me on Monday about local testing with Riley and the club on Friday. I phoned up Riley, and basically what he said is that they don't have access to the facility to do the testing on Friday. And so the online test is, I guess, what we're going to have to do. He did say that if you wanted to test locally, he could probably accommodate you in a home somewhere with a couple of testers. So, do you have Riley's phone number?
Uh-oh.
Did we lose Sarah?
No, I'm still here.
Okay, you were frozen there for a second.
Oh, okay.
Do you have Riley's phone number?
I know how to
You know how to get
reach
in touch
him.
with him? Okay.
Yeah, W7RL. I actually sort of looked at my calendar and just went, I think I'm gonna and I've started working on this July test questions at Ham Study
Okay.
rather than trying to do it Friday, because I would think I wouldn't do. I think I'm not doing anything, but then when I sit in class all day, half the day, it's like, oh, I'm way behind on other stuff. So, I'm just gonna probably test. Well, I'm looking at the calendar and thinking, I don't know when I'm I don't know the next Saturday or Friday I'm in town.
If
Second
you have
Saturday or
if you have a
second
reliable
Friday.
connection, you can just do it online on Friday.
Scott, I have learned that.
I'm just saying you could. But,
yeah, I have learned that my brain has not transferred to online learning and test taking.
Like my kid.
Well, when I'm teaching, when I was working with kids and adults, it's like you look at the problem on the screen and it doesn't make any sense, and you write it down and you go, "Oh, I was an idiot."
Yeah.
And I don't know if that's something that happens way earlier. I just have to work with it more. But I just decided what I can be a Luddite.
Well, it's important to know. It's important to know what kind of learner you are. So that's good.
Yeah, we're analog learners, not digital learners.
I'm both. I like Zoom. I like Zoom meetings because I don't have to travel.
Yeah.
Right. Well, yeah, there's and there's a difference between learning and meeting and test taking.
That's true.
And there's apparently is a difference between how your brain processes things that you write and how your brain processes things that you just read.
I totally agree with that. If I write it, that's actually the best way to study is write something down.
That's what I did.
Yeah.
That's why my notebook looks like a mess.
Yep. Like every notebook I ever had in school.
Yep.
Oh, I did that. I took a practice test, and the questions I missed, I wrote down, and I studied them.
All right. Well, it's 8 o'clock. Before I forget, we're a little bit small today, and I don't know why, but hopefully people can still join. And so is there anybody who had any questions about the exam on Friday if you're going to be taking an exam? And I know, Allison, I guess you had sent JD a note about exams, and I don't know if that's resolved or not.
I think it is, because I ended up signing up for it, and then the requirement, he sent me the requirements of basically having to have multiple devices for all the angles and cameras and space needed, and I don't have that here. So I said thanks but no thanks, and I found a local place here in Florida that I could physically go and do.
Oh, okay, good.
Because the other people that I talked to that did the exam online just needed like a tablet like I'm using for class, and they want like a desktop laptop plus cell phone plus empty house plus stuff, and I just don't have that.
Okay.
So
all right. But yeah, I'd say follow up with JD and just make sure it's all good. Okay, let's see. Well, I actually was doing a little bit of research this morning, and I thought that this would be, because there was a little bit of question as to whether or not a wave, whether or not an electrical signal can have DC and AC together. So I went out, and as a way of looking at this, if I can find it, I have I went and where did I put it? I'll have to find it now. Share screen. I probably closed it. And anyway, there we go. There we go. Okay. Now I get to share. So when I look at this, okay. Can everybody see that?
Yes,
Yes.
Okay.
Yep.
Okay. So the thing on the left that says VI, what is VI? What does that look like? What kind of voltage source?
AC.
AC. Okay. VC up above is a DC source. So what is interesting to note here is that if we were to just have, I'm going to turn on my annotation here, and I think this is a little bit of a good use of time. If I have an AC source, and here's my 0 line, I have a positive part and a negative part. If I were to just take that and run that into this transistor right here, and it went like this, up and down like that, the transistor needs to see what kind of voltage, considering this is a silicon transistor. What kind of, how much voltage does it need?
0.7.
0.7 volts. So if this went up to like 5 volts and this went to minus 5 volts, would that transistor always function?
No.
No, it wouldn't. It would actually only function in the part above. Now, if I were trying to make an actual replica of this signal, because that's what an amplifier does, it makes a copy of something. If I were to try and make a replica of this signal, what would I get if I just ran that into it? I would only get the top part, right? Does that look like a replica of that signal?
Nope.
I would say no, right? So what we end up with is the fact that we somehow have to take this signal and raise it so that our 0 voltage line is somewhere else. So here's our 0 voltage line. And we're going to take our whole signal and boost it up so that it's all positive. The way we do that is if we were to take a look at how this signal goes through, this is AC. What happens when AC hits a capacitor?
Charges it up.
It goes right, but no,
Okay,
AC goes
yeah.
right through.
Right through it. Yeah. It's
Right.
like a short. Yeah.
Right. AC goes right through. So the AC makes it in here. AC goes down through here. AC goes down through here. And then some of the AC goes down through here. That turns into a filter of some kind. And now we also have AC being switched by the transistor, and it comes out over here. Well, that's good because now we have AC coming out of our little amplifier. Well, that's really good. But how do we boost that? The way we boost it is, how about the DC that's coming out of here and going this way and this way? Well, remember these two resistors? That makes a thing called a voltage divider. So by using those, we can select a portion of the voltage that's DC to be boosting the signal right here. And because this DC also flows this way, what happens when it hits the capacitor?
It would charge the capacitor then.
And then do what?
Stop it.
Nothing. That's right. It doesn't go through. Same thing over here. The DC goes this way and hits this capacitor on the right. And what happens to it?
Nothing.
Nothing. It
I mean,
stops.
it charges. Yeah.
Right, but that's it. So for the DC circuit, the whole circuit is basically this. That's the DC circuit. There is In other words, for the power supply, it's like that little box. And what we've managed to do is take AC and pass it in so that it gets to play in DC land. And then on the output, we take whatever AC is in there and we pass it out. And it goes out into the world again.
With no DC attached.
With no DC attached, because the DC can't make it through. So our signal that goes in ends up being amplified by the transistor and then passed out with no DC. So if we have a signal that looks like this, what we get out is a bigger copy of the same thing, which is exactly what we want when we do an amplifier. We just want to make a bigger copy of it. But there's no reason for us to move DC current around because, you know, that's not interesting. So
But the part of the exercise was to smooth out everything on the bottom half of, you're trying to elevate the whole thing to the higher scale.
we're trying to put it. So let's say that our signal looks like this. Let's say we're using, let's say this is our voice, right? Our voice goes on the positive side and the negative side. You can't put that through a transistor by itself. It won't work because a transistor doesn't work down here. So you cut off that portion of it. So the key is you have to move it up, which is the same thing as basically moving the 0 down to here. So that this entire circuit, this entire signal, which is the interesting part, this is your voice, is now exclusively in the positive. You've basically added a DC offset or bias to the signal to move it into a place where the whole thing is now positive. It's sort of riding on a waterbed, if you want to think of it that way.
Yeah, that makes perfect sense.
And then when you amplify it, you get something like this. You get something bigger, which is an exact copy and hopefully never goes below 0. But then the whole thing is still above that line. So then you have to drop it back down to the 0 line where you can do something else with it. So then it really still does do pluses and minuses.
Why do you have to bring it back down after you've gone all the trouble to move it up?
Well, because what information is there in the fact that something is offset by 5 volts? What information is it? If you try to use that to run a speaker, what will that do? It'll just heat up the speaker, right? I mean, the speaker
Whatever you
is,
say, Professor.
yeah. Well, I mean,
I'm lost.
okay.
If you have positive, negative, you don't have a proper frequency signature, right?
No, it's still there. So let me ask, what if I do this? And I have it here. How is this different from this?
In the upper one, you have negatives as well as positives.
That's
In the
right.
upper one, you just
If
have
I am using that to run a speaker cone, what is a speaker cone? It's a coil. What will this do if I try to run that speaker cone?
Overheat it.
It'll overheat it. Yeah, there's no reason to have that bias there. There's absolutely no reason. It does no good. We are just simply adding it during the amplification process and then taking it away because it doesn't do me any good as far as the information that's on it.
So the reason for elevating the wave above the 0 plane is just for the sake of running the transistors properly.
So here is what a transistor's input output curve looks like. Here's our input voltage. And here's our output voltage. Okay, so there are 3 regions. There's something called cutoff. And remember we said that a transistor has to have 0.7 volts to start working?
Yes.
0.7 volts, right there. If our input voltage is below 0.7 volts, it doesn't amplify anything. So we get nothing out. Well, there's a point at which when you get to saturation, let's say it's at 3.5 volts, whatever it is. It doesn't matter how much more you put in, you're not getting anything else out. You have exceeded its ability to do anything. Inside this region, this is known as the active region. And in some portions, you can actually say this is a linear region where a proportional input change, an input change delivers a proportional output change. If you are trying to amplify something and you get an input value of 6 and you want a value of 12, if you get an input value of 9, you want an output of 18. If you get an input value of 3, you want 6. Would you say that's a linear function? In other words, every time you put something in, you expect something double to come out. That is the definition of a linear function. So that works only in this range. This is true with vacuum tubes also. Vacuum tubes need to be forward biased in order to work properly. So to basically take this transistor and put it in a state where it can actually do something useful, you need to boost whatever the signal is. So let's say the signal looks like this, to get a signal that looks like this coming out. So here's your bias point. Here's your bias point. These should translate to each other if I did it right. And then you can remove it and shift this back down to 0 and shift this back down to 0.
I guess I'm having trouble understanding why after you go to all the trouble to move it, you would unmove it.
Okay,
Or
let's say
done.
you're using a vacuum tube amplifier and you need 800 volts to 800 volts to put it in the middle on a vacuum tube. Do you really want 800 volts carrying no information going into your antenna? If it's doing nothing, how much information is there on DC? What is this telling you? It's telling you a single thing. It's telling you there's voltage there. Is there any information there other than that?
No.
No. And if your signal is always above 0, let's take a look at an antenna. Well, when it's plus, the current flows this way. And when it's minus, the current flows this way. What if it's always plus?
It's a one-way street.
How are you going to move in? How are you going to move anything? And the answer is you can't. So you have to shift it back to a place where you can do something with it.
When you move that down, it creates information. Because now it's positive.
So
Okay.
the
Take
reason I bring this up is because right now, today, we are getting into a signal, a portion of the class, which is called, let me get down to that part. Let me find it. I lost my place. HF propagation. We did that. We are in a section that's called amateur radio signals. And here we go. Amateur radio signals. Okay. Modulation modes and signal bandwidth. So if you take a look at a sine wave, right? So we're going to draw a sine wave. And we're going to say this is at 21 megahertz. And it is only a pure frequency. In other words, it's not changing in time. What is that telling you? I mean, if you look at it, what do you know? What information do you know? You know, there's a signal there, right? You know what the frequency is? You can measure it, right? You can measure the frequency. You can also measure the amplitude. But what if it never changes?
You just get a tone.
You just get a tone. What information is there if I do this and go on forever? There's no information on it other than the fact that it's there. That's a very boring signal. So things that I can do with this sine wave. What can I do with this sine wave? How can I change it?
Change the frequency and the amplitude.
I can change the frequency. What else can I change?
Amplitude.
Amplitude. So I can do this with it. Okay, what else can I do with it?
I
Phase
suppose
shift.
flatten it out.
Yeah, I could flatten it out. That's a change in amplitude. So I could change the frequency. I could change the amplitude.
You just showed us how to offset it or bias it, I think is your word.
I could, but that doesn't really change the signal itself. So what we're looking at now is changing the signal to make it more interesting. How else would I change it?
Phase shift.
I could phase shift it. I could do this. I could be doing this. And at some point right here, I could say, you know what? I'm actually going to make a jump so that I jump to down here. This is discontinuity, isn't it? Right there, it made a jump from way up here to way down there. That would be a phase shift. Other things I could also do combinations of these things. So if I do these things on purpose, if somebody's looking at it on the other end, what could they figure out?
You're a geek having a great time.
Well, if they saw something happen to it, what does that mean?
Well, they would know you did something.
They
so
would
could
know I
figure
did
out what you
something.
did.
Exactly. If I told them everything that I did meant something, they could see what I did and figure out what it meant. This process of changing it is known as modulation. The process of undoing it, figuring out what it was, is called demodulation. What's another thing I could do with this signal right here, the original signal? I could do something very, very simple with it.
Turn it off.
Turn it on and off. Yeah. What's that? That has
Morse
a name.
code.
That's
Yeah,
Morse.
there.
We use Morse code. That's actually called CW, which is continuous wave. And just by turning it on and off, essentially we're changing the amplitude by completely shutting it off. So all of these are forms of modulation and demodulation. And if you put these two words together, you get something called a modem. Mod, demod.
Oh, that's where the name came from.
That's what a modem is, a modulator, demodulator. Okay, so now we've established that we can make signals more interesting by doing something to them.
So when you say constant wave, is that the flat line?
Continuous wave. The continuous wave is a continuous frequency that we then interrupt. Okay, so what type of modulation?
Oh, so every dot and dash is just a different length of an interruption.
That's exactly right. And in
Is it
fact,
really?
if you look at it in time, it looks like this.
So which one's which?
So this would
So
be a da,
interruption.
and this would be a dit. So this would be,
And then the constant is the flat line in between.
well, that's the delay in between them. So this would be da, da, did it. When you listen to it, that would be a letter Z.
But technically, there's quiet in between each
Yes.
of those sounds.
Yes, this is actually known as OOK or on-off keying. You're just basically modulating it by turning it on and off, which is why CW transmitters are so easy. You just need an oscillator that you turn on and off. That's why CW is a really easy transmitter to build. There's virtually no, I mean, there's no modulation more than turning something on and off.
So the DAs and the dits are the actual frequency, and then the OOK is the off period, however brief in between them.
This is the, okay, so you have a couple of things. You have a carrier frequency, and then you have a tone. Well, no, actually, you just have a carrier frequency in this case. You just have a carrier frequency, and we're going to get into why you can actually hear it shortly.
Okay.
Okay, so type of modulation used for VHF and UHF voice. FM stands for
Frequency
frequency,
modulation.
and PM stands for
After dark,
phase modulation.
whole face.
For VHF packet radio, which is basically digital over VHF, FM or phase modulation. So in order to generate that, we use something called a reactance modulator. And to demodulate it, we use a frequency discriminator because we're looking at changes in frequency or phase.
Back up a question.
Yep.
Are those the same answers on two questions consecutive?
Yes. Can you believe that? Because
No.
it's voice as well as VHF packet, because packet is FM. It's used over repeaters, or it can be. You can use a handheld radio, an FM radio, to transmit data over packet. So they're both FM or phase modulation.
Okay.
Okay, amplitude modulation. So AM is literally just amplitude. So here's our original signal. This is our carrier. And then what we can do is we have something called an envelope, which is basically your voice, which is a much lower frequency that goes like this. And what we do is we shape our internal wave, our carrier frequency. We change its amplitude. And now we have that. And then this goes away and that goes away. And that's now our amplitude modulated wave. It gets louder, it gets quieter. The amplitude changes in time. Does the frequency change?
No.
Nope, just the amplitude. Okay, so that's AM. Now, the interesting thing about AM is that if you were to look at it, and we're going to start drawing things in a slightly different way here, we have a frequency of 0 to infinity. So this is now a frequency chart. We're going to be using this a lot. This is our carrier frequency. Notice FC. That's our carrier frequency. That is the red frequency. That's the frequency that makes this particular wave. What we're going to do with this now is, because we are modulating it, we are going to end up with something called modulation sidebands. If we were to look at this on a frequency spectrum chart, it would actually develop sidebands. This is the carrier frequency. There's some energy in that frequency. Now, this is now a different way of looking at things. This up here is the time domain, and this is the frequency domain. So in effect, by modulating the amplitude, we have actually essentially created changes in frequency. We've actually created things that have a different frequency, that are slightly different from the carrier frequency. So with typical voice is nominally has a frequency range of 0 to 3 kilohertz. So 0 to 3,000 hertz. That's the range that basically covers most of human voice. By doing this, what we have is FC plus 3 kilohertz and FC minus 3 kilohertz. We actually spread out within that entire range based on the voice profile that is making that signal. So if you have a very bassy voice, what will happen is it will be more concentrated toward the center. If you have a high-pitched voice, it will be covered all the way to the outside. What's important to note about this is that from end to end, this covers 6 kilohertz or 6,000 hertz. So how do you think we could actually build a receiver that would look at just these frequencies? What would we use to filter out everything outside? Because we don't care about it. What do you think we would build? I'll give you. That'd be a bandpass filter. That's exactly right. That'd be a bandpass filter. And in
That
fact,
thing when you called a notch yesterday,
No, a notch would be like this. That would allow everything but one. So we're building a bandpass. We are selecting components so that we get a certain range of frequencies through that's about 6 kilohertz wide. That's an appropriate filter for an AM signal. So now
Scott,
if we were to
AM or FM?
AM, that would be AM. So what we also have is the fact that these filters are not perfectly square. So we're going to make sure that that's not perfectly square. It actually looks like this, and with a little bit of bouncing in between, like that. And in fact, there is something in a filter called a half power point or a 3 dB point. Why is it called 3 dB point? What's half power? 3 dB is also known as
Doubling.
half power. So this right here is the 3 dB bandwidth of the filter. So basically everything between one end and the other that's 3 dB or higher makes up the bandwidth of the filter. There's also, when you put this in, if the original signal is, let's say, up here, I'll use a different color. So the original signal is at this level, and when you put the filter in, because nothing's perfect, the output is actually dropped down slightly. This is known as the insertion loss of the filter. Basically, by putting it in there, it drops the signal down. And how do you think you measure insertion loss of a filter? What units?
dBs again?
dBs again. dBs show up everywhere. Yeah. So insertion loss is measured in decibels also. Okay. Well, now we've established that we have a signal, which is AM. And we're going to erase this. And we're going to erase that. We know that it's 6 kilohertz wide. And okay. So now here's the next question. Let's take a look at this signal right here. So this is AM. Now we're going to do something with this signal. And we're going to look at this and say, okay, what information is there on the carrier frequency? A carrier just looks like this. If we are the receiving station, what information is there on just a frequency within a signal of one frequency that doesn't ever change? We already talked about this. There's no information. There's no information. It does nothing. So this carrier provides no info whatsoever. But what does it do? You have to make it, right?
It's a carrier. It's a highway, right?
Right. But let's say that you have AM and then you run that through an amplifier. What are you also amplifying? If you're putting it through, let's say, 1,000-watt amplifier and your signal looks the same way, like this, right? It's that signal. And now you're making a 100 times bigger copy of it. What are you also making 100 times bigger?
Carrier.
The carrier. What information is on the carrier?
Nothing
Nothing. It sounds like a big waste of power, doesn't it?
so far.
Yeah, it does sound like a big waste of power. So what we can do is we can, through some creative filtering and through some creative filtering, we can actually take this signal and we can X out the carrier. And that's known as suppressed carrier. So our signal is still how wide?
6K.
6,000 hertz. But now when we amplify it, are we amplifying a carrier frequency?
No.
No.
Saves a lot of power, doesn't it? Because now all that 1,000 watts is going exclusively into the information, right? Into your voice. Well, that's pretty cool because we just made it more efficient. But now let's go one step further. The upper sideband.
It's 8:31. Good morning, pal.
Hold on. Why do I have that open? Oh, I hate this. There we go. The upper sideband and the lower sideband are mirror images of each other. When we did the modulation, we ended up with an upper sideband and a lower sideband, which have the exact same information. So if they have the exact same information, do you have to send both of them?
Theoretically not.
No. So let's kill that one and we'll select upper sideband. So now how wide is our signal? It's half of
3,000.
6.
3.
Now it's 3 kilohertz. And it only has that information, which is the exact same as what we really wanted to send in the first place. So when we amplify this, all of our energy in our amplifier is going into amplifying no copies,
Connection.
right? No wasted power and no bothering sending out a bigger carrier because nobody really wants it. And now we have something called single sideband. So the difference between single sideband is that it's way, way, way more efficient than AM. This came about in roughly the 1950s. Before that, everyone was using AM. The tricky thing, of course, is that if you have a reference point, which is the carrier, you have a reference point for your signal. Your receiver will hear the carrier energy and actually use it to generate sound when you do demodulation. But if you take that away, your radio no longer has that reference point. So let's say now that we're going to take our single sideband signal, which looks like this. Here's our frequency. Here's our carrier frequency. Your single sideband looks like that. If your radio is tuned to right here, your single sideband signal, which is 3 kilohertz wide, will sound perfect. But what if your radio is tuned right here? What will happen?
You're gonna lose some of it.
Has anyone operated single sideband, Max? What did you experience this weekend, Max? If you're tuned off frequency?
Yeah, a very strange voice. Yeah, it's very high, very low.
Or it could be really low because you could be tuned here.
Right.
In which case all the pitches would be way too high. If you're on the red line, all the pitches would be way too low.
Right.
And there'd be something on the other sideband, right? Because it's down now on the backside. So you have to tune single sideband very carefully. And you also have to you have to create your own frequency inside the radio. And this is known as a beat frequency oscillator. You have to get
frequency oscillator.
Beat frequency, BEAT.
Oh, beat.
What does a beat frequency oscillator do and why do we need that?
Okay, it gives you a reference point to say, here's my 0 point.
Oh, okay.
That stuff that's over here is supposed to sound like something. So now this is the next step. We have our BFO over here, and we have the input from the antenna. This is a device called a mixer, and the mixer takes this signal and combines it by adding and subtracting frequencies. So if I have carrier frequency plus info, and I have carrier frequency, FC, coming into it, I get sums and differences. I get sums and differences. So I get 2 times the frequency of the carrier plus the info, but I also get carrier frequency plus info minus carrier frequency. And what happens when I do that? Those cancel out and I just get the info back. So if I pick it right, I get it back. Here's the last trick. Because this device does all the sums and differences, I get a signal here and here and here and here, all the different additions and subtractions. How do I get the one that I want? How do I pick it? What do I use?
Tuner. The tuner.
Nope.
Oh, the filter.
I use a filter. I design a filter which can accept these frequencies, which contain the information that I want, and I reject all the other ones. So this is known as the ultimate rejection. The amount of rejection that I get is known as the ultimate rejection. And usually, if I do it right, these are on the order of, let's say, 60 dB. So how many times is 60 dB?
6.
It's 20 times 3 and 6 times 10, and 10 was doubling, wasn't it?
Right. So, well, yeah, no, 10 is 10 times. 10 plus 10 plus 10 plus
60.
10 plus 10 plus 10.
That's
And
right, it's 3
and-
that's doubling.
Yep. And every time I get a 10, how many times is that?
10 times.
10 times 10 times 10 times 10 times 10 times 10 is
10, 100,000, 10,000, 100,000, million.
those
Mhm.
signals outside of my outside of my filter passband are attenuated 1,000,000 times. I get 1/1,000,000th of the amount of signal outside the passband that I wanted. That worked pretty well, right? Filters are awesome. Filters are really cool. Filters are an essential part of your cell phone, of every radio that exists, of every television that exists. Okay, so
filter
now
filters out every frequency except the one you want. Is that right?
you have selected what components to make that happen.
So is a mixer and a beat frequency oscillator the same thing?
They are not. A mixer uses a beat frequency oscillator.
A mixer uses.
Okay, so here, ready?
uses.
Ready? We're gonna do something right now. So a mixer is a nonlinear device that adds and subtracts frequencies together. So let's say that I have a tone. Let's say I have a carrier on 7.006600 megahertz. Right? And it's just a carrier, but it's Morse code. I tune my radio to 7.006000. This is my beat frequency oscillator. I tune it to that. What will I get out? 7.006000 minus 7.006. Sorry, that should be 600 minus 000. What do I get?
Nothing.
0.000600 megahertz. How many hertz is that?
6.
Well, it's 0. So we're going to go 1, 2, 3, 4,
0.6.
5, 6. That kills the megahertz, 600 hertz.
Okay.
What does that sound like? Everybody here want to hear what that sounds like?
It's a low tone.
It sounds like an A note, but a little higher.
Well, a 440 is an A note, right? So,
Right.
Uh,
So
let's
maybe
see.
a C note?
It's almost a fifth. It's almost a perfect fifth. 660 would be a perfect fifth. So let's see. We're going to go to and hope I can hear something. I'm going to share it now.
It was 1,000 megas a million. That's why he went 6 decimals.
Okay, let's see what we can find. There's one. We would hear that.
Morse code.
If I had a modulated signal with Morse code and I tune my radio so that it's slightly off in frequency, the pitch that I get is the beat frequency. And if I change my tuning frequency slightly, notice what I get.
Down.
A little more. I'm basically changing my beat frequency oscillator. Now, let's do the same thing over here. Notice that we're getting a nice audible tone, something audible here. Listen what happens if I mistune this. Or go the other way. And that is the impact of tuning. And that's why when we inject our own beat frequency into it, if the beat frequency is not quite right, we get something that doesn't sound quite right. Okay, so now let's take a look back at our frequency chart that we're going to make. Now that we've beat FM, we beat AM and single sideband into submission. Yeah, go ahead. Now we're going to talk about FM. So we have the same kind of thing. We use something called a frequency, a reactance modulator to make it. It basically takes our voice and causes the frequency being generated to shift. We use a frequency discriminator on the other end. And what we end up with is we have our carrier frequency. We end up with a whole block of frequencies that are, instead of being made by the amplitude, they are made by the frequency of the modulating signal. So they fill this entire block. So when this signal gets to the receiver, what happens is this signal, instead of looking at, the amplitude of it, this looks at what frequencies make up this signal. It uses something called a discriminator. To look at those frequencies and say, okay, well, it contains these audio frequencies, and then it amplifies them and puts them out into your speaker. So it's a reactance modulator to make it. And a discriminator to listen to it. An FM signal has a bandwidth of 10 to 15 kilohertz. Now, why don't we use FM on lower frequencies? Because they take up 10 to 15 kilohertz, which is 5 times as much as a single sideband signal, and not a very efficient use of space. That's bandwidth. And since bandwidth is the amount of room we have on a band, let's say we had a 15 kilohertz wide signal and we were on the 7 megahertz band, which is 40 meters, which only runs from 7.000 to 7.300 megahertz, or 7,000 kilohertz to 7,300 kilohertz. If that were true, that one signal would take up about that much room. Not a very good use of space. But on the 2 meter band, where we go from 144 megahertz to 148, it takes up about that much room because the band is so much bigger. The other thing that is important to note is that the more information you put into a signal to modulate it, that is what modulation is, the wider the signal becomes. So here's kind of an interesting question. If I were to look at Morse code, how many tones, how many different carrier frequencies make up Morse code? A Morse code signal. All I'm doing is doing what? Taking it.
One frequency, right?
One frequency. Yep.
Wave. Continuous wave.
Yep. If I were to look at this signal on a frequency chart from 0 to infinity, I would actually see, here's the center frequency, and I would see this. Wait, that doesn't make any sense, right? Does that make sense? That it would actually, instead of just being the tone, the center frequency, that it actually makes sidebands?
Well, didn't you say that's by definition, all frequencies have a sideband?
No. I mean, if I just had a signal that looked like this, and it went on forever, what I would see was just this. But when I turn it on and off, I get this.
Because of the process of on and off.
Yeah. And in fact, the faster I turn it on and off, if I go faster, I'll actually have wider sideband. Now think about that for a minute.
Now, is that pouring more power into it or
Nope.
more?
No, it just
No.
means that it spreads wider. If I have Morse code and I send really fast versus really slow, I might have sidebands that are out to here. If I send really slow, it might be only here.
It's like creating a wake with a boat.
Yeah. So this actually comes from something called information theory.
Very small one.
Yep.
This is that fast and slow a function of the operator or the
Yes,
transmitter?
the operator. The operator. Now, the other thing, of course, is that depending on how fast the modulation envelope changes, if I did that versus this and made it really, really steep, the reason that it makes sidebands is because we are putting information into it. They have to be carried somewhere. And information theory says that it has to go somewhere. They actually go into modulation sideband. So even though it's a single carrier frequency, being turned on and off, the act of turning it on and off makes it take up space. And the amount of space that Morse code takes up is proportional to how fast you're going. So Morse code typically will take up about 150 hertz of space. Now, again, single sideband will be about like this, 3000 hertz. AM will be about like this, 6000 hertz. FM is about 10 to 15 kilohertz wide. So if you look at efficiency of space, which of these is the most efficient way to use your bandwidth, considering that bandwidth is a shared resource?
FM.
I hope not.
Well, CW.
Morse code. Yeah, Morse code is a very, very narrow band. Now, there are other ones even. There's one called PSK 31, which is a digital mode that uses 31 hertz of width. And what that means is that for every one of those signals, you basically take bandwidth and you can pile signals right next to each other. Like I could put another Morse code signal right here and another one here and another one here and another one here. And I could use that same 3 kilohertz of bandwidth that I'd use for sideband and put 20 Morse code signals in there. Now, the other thing that you can do when you do something like that is, let's say that I am using a receiver and I don't want to hear anything but this one in the middle. I can do a filter that does that and eliminates everything outside, which means I don't have to listen to all those adjacent signals. So a typical filter for Morse code, it would only be 500 hertz wide. It would basically eliminate most of the external signals, whereas a filter for single sideband would be like 1800 to 2400 hertz wide. All right, so any questions on this?
Is AM wider than FM or is FM wider than AM?
FM, well, it depends how you modulate it. FM can be wider than AM and AM can be wider than FM, depending on the modulation scheme. So
Okay,
another way to look at this is that if I am doing FM, typically we modulate FM. We don't modulate at 144 megahertz. What we do is we modulate a signal at, let's say, 12 megahertz. And that's our carrier frequency. And we take this, actually, I'm not even going to say 12 megahertz. We're going to say that we have a modulator that is making a signal that's like 416 hertz wide. That we're using our voice to do that. And we take this through a frequency multiplier, which multiplies it by a factor of 12 and gets us a signal that has a little bit wider width. Actually, that should be kilohertz. And that makes a signal. No, that's wrong. Darn it. Sorry about that. 416 hertz. And that gets a signal that's about 5 kilohertz wide, above and below. So this is known as a frequency multiplier. So this is our modulator and this is our output. And we use this 5 kilohertz to modulate our transmitter frequency. So that is why that's why FM usually takes up more space, but you can be doing a very narrow band FM. For instance, if you had a modulator that only did 100 kilohertz wide, you multiplied it by, why do I keep doing that? 100 hertz wide, then you multiplied it by 12, you'd only get 1.2 kilohertz. So what do you lose when you do that? What do you think you lose when you do that? You're taking the same voice and you're packing it into a narrower space. What do you lose?
Information, quality.
Quality, yeah. So if you look at an FM radio station, what is the bandwidth of an FM radio station?
It's wider, and that's why they send out music on FM and voice on AM.
That's right. So like right here, this is a right here, that is a single sideband signal. Notice how wide it is. Takes up about 3 kilohertz. We take a look at that Morse code signal. Look at like down here. And it has a little bit of width, but not much. FM would basically, the FM that we're doing would fill up about,
Top one.
it'd fill up about 4 times as much room as this voice signal right here. And FM on the radio would fill up literally this entire space. The whole frequency band that you see here, FM on the radio, because it has a bandwidth of about 200 kilohertz because of the desire to send high fidelity, just takes up that much room.
Was that a website you were showing us just now?
That's actually websdr.org. It's that's the University of Twente in the Netherlands. They have a digital signal processing or software defined radio that's listening to everything at once. That's websdr.org.
Got it. Thanks.
Okay, which of the following is a form of amplitude modulation? That would be single sideband. Okay, on the VHF and UHF bands, because single sideband takes up less space than FM, it also does not suffer from something called the capture effect, which is that below a certain signal strength, FM just sort of falls apart. Single sideband, you can actually hear it get louder and quieter. So even if the signal is, starting to deteriorate because the signals are really weak, you can still hear single sideband. So for weak signal contacts, we typically use single sideband. Okay, so if we're looking at which sideband to use, we have a choice because our transmitter can make upper or lower sideband. We pick upper sideband on the 10-meter band. And in fact, if you look at the frequency spectrum chart, you will see that we have frequencies from basically 1 megahertz all the way up to, all the way almost up to light almost up to infrared light. The break point is roughly 10 megahertz. Below 10 megahertz, we use lower sideband usually. Above 10 megahertz, we use upper sideband. So that's the break point. Single sideband compared to FM is narrower. Approximate bandwidth of a single sideband signal is 3 kilohertz. A VHF repeater signal, 10 to 15 kilohertz because it's FM and that's what we use. Disadvantage of FM compared to single sideband. Has anyone ever heard of something called doubling on a repeater? You doubled.
Two
and-
people at the same time, yeah.
Okay, and if they're the same strength, who wins?
Well, nobody, it becomes. a
That's
mess
right.
at the
You
same
can't hear
time.
either one. That's caused by something called the capture effect. And only one signal can be received at a time. This is why AM is still used for aircraft. Because if there's a weak aircraft that's calling for somebody on the same frequency as a strong one, you can still hear that there are two of them. That's why they don't use FM on aircraft. AM, fast scan TV. This is NTSC television. We are actually allowed to use television. It's called ATV or amateur television. And yes, it really does fill up 6 megahertz of bandwidth. So the question then is, why don't we use this on all of our different bands? Why don't we use this on all our different bands?
Because it uses up so much bandwidth, you'd never be able to talk to anybody.
That's right, 6 megahertz. So let's look at different frequencies. 10 megahertz, we have 28 to 29.7. We only have 1.7 megahertz of space in the first place. Well, 50 to 54, that's only 4. 144 to 148, that's only 4. However, 420 to 450, we have 30 megahertz of space. And in fact, 420 megahertz is a television station, television frequency. So is 426. Notice it says amateur TV fast scan, the light blue. So on frequencies where we have more space, we can do television. We can do 6 megahertz wide television signals. And people do. Okay, next. Morse code, approximate bandwidth of about 150 hertz. CW is another name for Morse code. It's one of the narrowest bandwidths that we have. And an electronic keyer, Max, you probably saw me use one at some point over the weekend.
Yep.
Is a device that assists in manual sending of Morse code by hitting dits and DAs and having the electronics send it for you. That way you don't have to pound it out yourself. Okay, digital modes. Okay, so all of those modes that we just talked about were analog. So now we're going to look at digital. Digital is basically ones and zeros, computer to computer. Morse code, actually, if you think about it, is kind of a digital mode too, because, you know, it actually encodes dits and DAs and by turning something on and off. Digital mode, packet radio, which is what you hear over your repeater. IEEE 802.11 is Wi-Fi. FT8 is a digital mode. Those are all digital. If we're doing packet radio, there's something called APRS, which is the Automated Packet Reporting System. It's a combination of global positioning system and real-time tracking with mapping over the radio. And so we use a lot of packet these days. Packet used to be used for bulletin boards before there was something called email. I actually had a packet bulletin board station in my dorm room in college. People could send me email through my packet station, which connected to my handheld radio because it just used FM. So packet radio has a checksum. It has a header that contains the call sign of the station being that's ending. And if something goes wrong, it says, I didn't get it, please send another one. So the answer to that is all of the above. ARQ is automatic repeat request. So notice automatic repeat request. ARQ is automatic repeat request. So error correction method in which the receiving station detects errors and says, yeah, I didn't get it, send it again. So it'll send an ARQ request and say, I need it again. All right, APRS, that's the automated packet reporting system again, which is basically packet radio with global positioning system and then putting the whole thing on a map. And when we get to break, I'm going to pull that up and then it'll be there on the screen when you guys come back. Type of data that can be transmitted by APRS, GPS position, text messages, weather data, speeds. This is often used for people in cars. They can track where they are. Essentially, the signals get picked up by something called a digipeater, which eventually makes its way to another station, to another station, to another station, which can be displayed on a map. PSK stands for phase shift keying. And why do we use phase shift keying? Because it takes up very, very, very little bandwidth. It's actually very efficient. So PSK 31, for instance, is a 31 baud, which is a 31 baud mode. 31 baud actually translates to about the speed at which you can type, which is kind of cool because it's a sort of like a very narrow bandwidth real-time mode.
Can you explain the term baud? What does the term baud mean?
Oh, a baud is from it's from Baudot, from the Baudot code. It's kind of like a piece of information, but it's specifically from Baudot code.
What's it a measure of?
It's a measure of how fast the data is coming.
Okay, thank you.
So even though it looks like that description is only 31 hertz, it's just a quinky dink that 31 baud is only 31
More or
hertz.
less. Yeah, more or less. Now, if somebody here has the exact origin of baud, I'd be glad to hear it.
I remember talking about baud rates in computers 50
Yes, exactly.
years ago. We talked about
A 300 baud modem.
Computer could process.
Right, a 300 baud modem or a 1200 baud modem.
Yeah, I don't care about the origin. I just wonder what it means. And you said it's how fast data is coming. That answers.
It's how fast data is coming. 31 baud is really slow,
It's
but
how many signals per second.
right,
There you go.
right. But essentially, like if you think about your old school modem that you'd like connect your computer, that was like 1200 baud. 31 baud is really slow, but it's about as fast as any of us can type. Now, interestingly, PSK uses something called varicode. Varicode is a system by which the length of a bit, for instance, an A might be 100101010, right? Because it's all binary. Well, varicode is such that an uppercase might be that, and a lowercase a is 10110. It's actually a variable length code. So given the fact that all the uppercase characters are given 8 bits and the lowercase characters are only given 5 bits, how do most people type if they're using PSK?
All lowercase.
All lowercase, yes, because uppercase actually slows things down because it has to send extra bits. Okay, DMR, digital mobile radio. This is voice over radio using digital techniques instead of analog, right? So a reactance modulator or a frequency discriminator, those are analog things for FM. DMR uses FM radio to multiplex 2 digital voice signals. So your voice is turned into a stream of ones and zeros and then combined on a single repeater channel. And there can be 2 of them done at the same time. And because it's time multiplexing, that means that channel 1 receives the first time slot and channel 2 gets the second time slot. If all the radios that are listening to that frequency are listening for slot 1, they will never hear slot 2, which means that you can basically double the number of people that are using a repeater. and that's known as digital mobile radio or DMR. WSJT is the weak signal Joe Taylor mode. It's used for Earth, Moon, Earth. That's known as moon bounce. We do weak signal propagation and we do meteor scatter using WSJT. And does everybody remember that really cool map, the propagation map that I showed you guys yesterday, where, you know, from one location, it showed all the connections that are being made?
Yep.
That
Mhm.
uses WSJTX. Those maps are made from people using this software. So really, really cool. So FT8 is a digital mode capable of low signal to noise operation. That is the famous FT8 that is used for all of these things which require weak signal. Mesh networking is you basically take a Wi-Fi router, and because Wi-Fi routers share frequencies with hams, believe it or not, they actually do. Wi-Fi routers share frequencies with hams. We can take, because we can modify equipment however we see fit, we can take apart a Wi-Fi router, boost the power, change the modulation scheme, and turn it into something that we can use that becomes a self-healing network. So we basically take old school Wi-Fi routers and we modify them with different firmware that make them operate differently. And that turns into something called an amateur radio mesh. All right, safety, we're going to buzz through really quick and then we'll take a break. So electrical current flowing through the body. If anyone's ever gotten a shock from something, it doesn't feel good. It can give you a burn. It can disrupt your cell function because we're really just electrical machines, and it can cause your muscles to contract, which can cause you to let go of something, or unfortunately, it could also cause you to grab onto something. In the United States, the black wire in a 3-wire 120-volt cable is the hot wire. So very important, black is hot. The green is ground and the white is neutral. How do you guard against electrical shock? 3-wire cords and plug. The 3-wire cord and cord has a ground wire. That's the round pin at the bottom. Everything goes to a common safety ground, and you install mechanical interlocks in all high voltage circuits. So if you build a tube amplifier that has a 3000 volt power supply, when you open the lid, it's a good idea to turn that thing off. So you install an interlock that turns it off. The purpose of a fuse is to remove power in case of overload. A fuse or breaker in a 120 volt circuit should be in series with the hot conductor only. You don't want to break the neutral. You don't want to break the ground ever. You only break the hot conductor. Why should a 5 amp fuse never be replaced with a 20 amp fuse? You're basically allowing excess current to flow and you can burn your house down. When a power supply is turned off, there was probably a filter capacitor in there somewhere, which charged up. And unless there's a bleeder resistor across the filter capacitor, what will happen is that the power supply will remain charged. You stick your finger in and you get 120 volt shock. Or bigger. Which of the following is a safety hazard of a 12 volt storage battery? You stick your hand into an area where there's a lot of hydrogen built up because the battery has been overcharged or over discharged, and you can trigger an explosion of hydrogen, which makes a mess, not only because of the explosion, but because it could blow up the battery. And a 12 volt storage battery contains sulfuric acid, and then you get a shower of sulfuric acid in addition to the burns.
I've been there and done that.
Have you?
Yep, almost lost my eye.
Jeez. Okay. You safety glasses?
Didn't have any back in those days.
Yeah.
I was giving somebody a jump start.
Yep. And that's why when you connect to one terminal, you always connect to the frame ground and not to the battery negative, or if you can. Because you don't want to have a spark if a battery is really
I always
discharged.
just went straight to the negative. That was a bad idea, my mistake.
Yep. Well, that's why they recommend going to the frame ground, because if there's a spark, you want it to be away from the battery. What hazard is caused by charging or discharging a battery too quickly? Overheating or outgassing. Okay, now we're at antenna and tower safety. If you're ever lucky enough to have a tower, yeah, this is really important. An important safety precaution to observe when putting up an antenna tower, look for and stay clear of any overhead wires. About a month ago, we had a very, very, very experienced ham who was helping some friends take down a rather large antenna on somebody's property. And he saw that there was this big antenna as it was coming down, start to get snagged on a guy wire. And he said, "Oh no, it's getting snagged." And he ran over to grab it, and there was nobody watching to say, "Hey, don't do that," because the other end of this antenna was about to hit a power line. And he was killed instantly.
Oh, no.
Yep. Happens all the time. Unfortunately, it's really important to know where those power lines are. It's really important to stay at least 10 feet away from the power line. Notice if the antenna falls, no part of it can come within 10 feet of power lines. Why should you not use a utility pole unless it's your own power pole? Even if it is your own, you probably still shouldn't use it because the antenna could contact the high voltage line. If you touch an antenna while it's transmitting, you can get an RF burn on your skin. Makes a nice little puncture hole. When climbing a tower, have sufficient training on safe tower climbing techniques. Use appropriate tie-off tower at all times, and always wear an approved climbing harness. So even with all of those things, when should you ever climb by yourself?
Never.
Never. About 3 months ago, there was a ham from Germany, DL6SAI, I believe. And he has a place in Curacao. And he was going up and working on a tower that was starting to rust out. And he was about, I don't know, 50, 60 feet above the ground when the tower decided to collapse. And he was wearing all the gear, but he was, the tower bent, and then it bent again. And he basically was hanging from the tower and died. So even if you do all that, you still have to have somebody there helping you. Important safety rule to remember when using a crank up. The crank up tower is not designed to be climbed unless mechanical locking devices have been installed or if it's retracted. If you're really lucky, you have a tilt over tower so you can retract it and then lay the whole thing down. A safety wire through a turnbuckle. Turnbuckle is used to tension guy wires. Guy wires are, the turnbuckle is threaded. When wind comes along, it causes the whole thing to vibrate, which causes the turnbuckle to untwist. You don't want it to untwist, so you put a wire through it to prevent that from happening. Always follow local electrical codes when installing something. When you're grounding a tower, 1 8-foot ground rod pounded into the ground for each tower leg, bonded to the tower and to each other. So if you have a tower with 3 legs, you have 3 ground rods and common and connection between all 3. When installing ground wires for lightning protection, you want short direct connections. When you are installing ground wires, you avoid sharp bends because lightning does not travel well around sharp bends. It would rather jump to the ground than follow a sharp curve, a sharp turn. What should be done with all external ground rods? You bond them together with a heavy wire or conductive strap. If you're using a lightning arrestor, basically a lightning arrestor is a little tube that fits into your cable that has an inert gas in it, usually argon, which under normal conditions will stay in its normal state, unionized state. But if there's a 20,000 volt spike, it will ionize the gas, which will create a conductive path, hopefully, for the lightning to go to your ground plate. Notice your grounded panel. And instead of going into your equipment, it will hopefully go down to a ground in the ground and save your equipment and keep your equipment from catching fire.
Scott?
Yep.
Does that mean you don't have to disconnect your antennas?
Oh,
Do
no,
you know
that's
what I
still a
mean?
better idea.
Okay, it's still, okay, thanks.
But what if you're not home?
Makes
But
sense.
what if you're not home when it happens? So,
So how many times do you connect and disconnect your antenna every day?
no, I mean, we don't, no,
Out here, we don't have lightning issues so
we don't
much.
really have much in the way of lightning to worry about, but once in a while.
Well, if
So,
I see a thunderhead go over, I'll unscrew my antenna to my HF, my coax to my HF antenna, but other than that, I leave it attached.
exactly, same thing.
Okay.
Okay, now we're into RF hazards and radiation exposure. What are radio signals? Radio energy is low energy. It doesn't have enough energy to ionize atoms, which means it can't cause DNA damage. Whereas X-rays, gamma rays, cosmic rays, ultraviolet, those have enough energy to cause chemical changes in cells. Radio waves are not 100% safe because, as we know from microwaves, microwave ovens can heat water, right? So they can heat tissue, but they won't cause genetic damage. If you're putting in a station, who is responsible for making sure that your station is legal? That would be the station licensee. Whoever it's under the name of is responsible for making sure that it's safe. So you can use computer modeling. You can walk around with field strength equipment if you really want to, or you can use this FCC OET Bulletin 65, which is basically a calculator. Now, fortunately for all of us, we don't typically have to go through the FCC bulletin. Instead, there's something called, on the HintLink website, there's a ham radio exposure calculator, which basically takes the FCC information and encodes it into an easy to use website, which makes it a heck of a lot easier. And I'm putting this out there in the chat right now. So when you go through this, you say, okay, average power at the antenna, 100 watts. Notice it says antenna gain in dBi. Remember from yesterday what dBi is?
Yeah, that's the imaginary one that doesn't exist.
That's the,
right?
right. And then there's also add 2.2 for antennas rated in dBd. So this is a practical application of that. It's in the FCC documentation.
Yellow paper.
Yep.
It's going up there.
Okay, so distance from the antenna to the antenna, we're going to say 10 meters. We're going to say we're at 146 megahertz and go. And so here's our safe limit, or sorry, here's our exposure limit in milliwatts per square centimeter. Uncontrolled means that somebody could just walk through and doesn't know what's going on. Controlled means that the environment is such that people know that there's RF being transmitted in that area. So what we're going to do right now is we're going to say, okay, a 5-watt handheld radio, and we're going to say 2.2 dB, and you are a half a meter away from it. And guess what? It's safe for you, but it's not safe for anybody else at a half a meter. Let's say that you're using your handheld radio and it's actually 0.2 meters from you. And guess what? Transmitting 5 watts, constant 5 watts, it's actually unsafe, even for you, which basically means if you can use low power on a handheld, you should. If you can turn the antenna away from your head, you probably should. Good stuff to know, right? So here's the other one. So now we're going to take average power at the antenna, and then we're going to take a break after this part. So here is a beam antenna. Anyone ever, sorry, here's a dish. Anyone ever seen a dish?
Yes.
Yes. Can you repurpose an old satellite dish as a ham radio antenna? Absolutely. They work great. They work great. Okay, so let's say that this dish antenna on a particular frequency gives me 30 dB of gain, and I have a 1-watt transmitter. If I am standing right here, how much equivalent energy am I exposed to right there? Because it has 30 dB of gain.
1,000 times, right?
So
10
30 dB is
10.
10 plus 10 plus 10, which is 10 times 10 times 10 times is 1,000 watts. So I'm going to go over here, back to my calculator. And I'm going to go and do this. Average power at the antenna is 1 watt. And the gain is in dBi 32.2. And we're going to be 5 meters away. And guess what? That is not safe. We're only using 1 watt, right? I mean, the transmitter is only a watt. What's making the difference here?
The antenna.
The antenna gain, that's right. So let's also now take a look at that. And we're going to use that same antenna and we're going to use it and we're going to point it at the moon. So now we managed to have gotten a 100 watt transmitter. And we're using that same dish. And we are now, let's say, 50 meters away, and we're going to see if it's safe. Guess what? At a distance of 50 meters, it is still not safe because we are now using 100 watts, right? And what's our gain? 30 dB, which is 1,000 times. 100 watts times 1,000 times is
100,000.
100,000 watts. So does anybody have any question as to why you need a license to do this stuff now? As a technician, you are allowed to do this. As a technician, that RF energy that you're putting out, instead of 100 watts, you can run 1,500 watts. Well, at 1,500 watts, what would your effective radiated power in that direction be with that antenna?
1.5 million.
1.5 megawatts. You can do a lot of damage with an effective radiated power of 1.5 megawatts. You can do a lot of cool stuff with it too, but you can do a lot of damage with it, which is why, because we're allowed to do all this stuff, this is why you need to get a license. Even if you're never going to do it, your license permits you to do it.
So how difficult is it to convert the dish antenna to ham use?
Not. What I mean, what can be the radiator in the dish? What's the simplest kind of radiator that there is? The
Just a wire.
simplest antenna.
Just a wire.
Just a wire dipole. A wire dipole at the focal point of a dish.
So Scott, that would be a highly directional antenna, right?
That would, yeah. But what if you're trying to work the moon?
Yeah.
If you're trying to do moon bounce, that's what you need. Okay, the definition of duty cycle is the percentage of time that you're transmitting. So 50% duty cycle would be on 50%, off 50%. Duty cycle is really important because it affects the average exposure to radiation. Notice that we said in that case it was 100 watts. Well, if you're transmitting 100 watts half the time, then you're actually only transmitting an average of 50 watts, which means that you can double your output power if you're right at the safe limit. Why do exposure limits vary with frequency? We're actually going through something at my kids' high school where I'm doing RF safety exposure limits. And at 6 meters, which is the 50 megahertz band, that is the maximum absorption frequency. So we went through and we're doing all of our calculations on that frequency band because we are really absorptive for some particular reason. It must be due to resonance at 6 meters or 50 megahertz than any other frequency.
So Scott, microwave oven is what, 2-point-something gigahertz?
Yes.
And you're saying that the body absorbs
RF. We as a whole person are resonant. Yes,
Okay.
more
So
resonant at 50 megahertz.
Right. So it's just water that is resonant at the 2.2 gigahertz or whatever.
2.4 gigs. And if we didn't happen to contain water, then it wouldn't be a big deal.
Right.
The thing is, we contain a lot of water. So RF exposure near an amateur antenna, frequency, distance, and radiation pattern, which we talked about. What can you do if you to reduce RF exposure? Relocate your antennas. You could also turn off your transmitter. Then it's not an issue at all. Anytime you get any new equipment or change antennas, you need to go through and do a recalculation. Okay, next up is station setup and operating controls, and we're gonna take a break. 5 minutes, and we'll see you all in 5 minutes.
Scott, I'm going to need to go voice only.
I copied you, John.
Thank you, Vic. I'm looking for the dial-in number for this Zoom session right now.
I'll stand by one. I may have that.
Got the meeting ID, got the passcode.
Okay, I'm looking at the email called class stuff, which may be the same one you're looking at. I don't see a dial-in number. Let me go to the
Okay.
Zoom. Let me go to the Zoom page and see if I can learn anything here. Nope, nothing there. What else have I got to play with?
Meeting. Join meeting. I've got the Zoom app up on my shoe phone.
Shoe phone?
Don't get it. Just do your thing. I'm on a break and I gotta do a couple of dishes. Oh, why don't I have this thing?
Where am I?
John, I'm not finding the anything here.
Pouring out there, baby.
All right, well, I'm back. That was a little quick. All right, so what
Scott,
was it?
do you
Yes.
have handy the dial-in number for Zoom?
I have a number I think I could find. Da-da-da-da-da-da-da-da-da. I don't know if this meeting is set up for it, but I can tell you what it is. And if anybody has any questions at any time, I'm happy to hear it.
I'm curious if the author of the book is already started on a new edition for the new questions.
That is a good question, and I do not know.
Fair answer.
Okay, so the number that
Month is when our question pool changes for the test, right?
say what?
The end of the month is when the question pool changes.
June 30th. It actually changes July 1st.
And the new questions are already published someplace?
They are. Let's see. Does he have, if I look at the study guide. And, you know, I don't see that it's out yet. I'm gonna send him a note. Maybe he did it and maybe he didn't. I know he's kind of retired, but
Well, that was the reason I asked the questions, because you said something about him wanting to retire at some point.
yeah, he did. Um, Okay, let's see. Dan Romanchik.
Prerequisites for zoning.
Whoa, 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 whoa. I guess it worked. John, that worked. Maybe a little too well.
Zoom support page, prerequisites for joining meeting by phone. Host account is pro or above. Subscribe to the audio plan add-on.
Really?
Yep.
Wow. I did not know that. Although I know I've had people sign into meetings, maybe not this one.
Yeah, it works with the Zoom app on a phone,
Okay.
which is what I'll use at 10 o'clock when I have to split.
Okay. So you're gonna be good.
I'll be good.
Okay. All right.
As good as I get.
Okay. All right. Well, let's see. Everybody ready to get back going? So, okay. So did everybody remember what it was that I was gonna put up on the screen? Because I don't remember what it was. I said at break, I'm gonna put it up on the screen. Darn it. I'm just gonna my brain is going too fast. I gotta make notes instead. Oh, yes, okay. No, that wasn't what it was. Well, I'm sure we'll get back to it. Okay. Operating controls. We're on to operating controls and setting up a station and things like that. Okay, station setup and operating controls. So this is basically how to set up a station so that it does something useful. And so there was some question as to using using WebSDR, and I'm actually going to use WebSDR quite a bit right now because this is a really good way to show you all how station setup works and how equipment works and things like that. So this is the WebSDR website. Notice that there are many WebSDRs set up all over the world. And I happen to like the University of Twente because they cover from one end of the HF band all the way to the other. So we're basically looking at 30 megahertz of bandwidth right now on the screen.
Which college did you say that
So
is?
this is the one that comes up all the way on the top, University of Twente in the Netherlands. So this is looking at the entire HF spectrum in Europe. So we're going to look at given what time it is, we're going to look at 7040 because you know what? Let's go to 20 meters, 14040, and we'll zoom in. And depending on what's going on, we will either see some stuff or not a lot of stuff. Sometimes it'll be busier than others. And I'm going to unmute it. Okay, so this is a pretty busy frequency right here, right? We hear a couple of different signals at the same time. One thing we can do is we can do this. We're basically shaping a filter so that notice we're narrowing it down. You can't hear stuff outside, sounds a little hollow. The benefit of this, of course, is that we can ignore all the other stuff. Now I can also move my passband so that this would be like a high filter. This would be a low filter. And this is kind of a bandpass because I'm only allowing a certain number of frequencies through in a particular band. Now, if I were to try to listen to a voice signal like this, let's see what it would sound like.
Listening to this Morse code always reminds me of Jericho.
Yeah. Okay, here we go. We're listening to a voice signal, properly tuned. What do you hear? And why do you hear what
Charlie
you hear?
Brown's mom.
Yeah, why do you hear what you hear? Because what?
We're only hearing part of it, and it's
Yep.
a wider band.
Same thing. If we only listen to a part of it, we're not getting all the information. You need the entire frequency band to be able to listen to a voice, because that's where all the information is. Let's see.
India United 5, Kilo Zanzibar United, calling DX, stand by.
And that station is in Italy. I can tell because of the prefix. Okay, so certain things that we can do. We can take this station and we can we can do this with it. What we're doing right here is we're increasing our selectivity so that if we were to listen to a Morse code signal, we would only hear like 1 or 2 signals. That's the definition of selectivity, to be able to select just 1 or 2 and ignore all the others. And okay, now here's the other one. Everybody unmute yourself. Everyone unmute yourself at one time.
Then do you want us to talk too?
Nope.
Check, mic check.
Nope.
Check,
On the
check,
count
check.
on the count of 3, I want you to say your first name. Ready? 1, 2, 3.
Jared.
Yep.
Okay, well, I think I heard Bobby May. But you know, that would be another way of thinking about selectivity. Like the ability to be able to pick out just one in a large group of things. Fortunately, on the radio, we can filter for those things. Now, Bobby May, since I heard you, what I want you to do is start saying something, you know, just say your name like 5 times, and every time you do, get quieter.
Bobby May, Bobby May, Bobby May, Bobby May, Bobby May.
Okay, you got to get even quieter to the point where you're whispering. Go ahead, 5 more times.
Bobby May, Bobby May, Bobby May, Bobby May, Bobby May, Bobby May.
Now I can. You got to get down to whispering because I can still hear you. I want to tell when you disappear.
Bobby May, Bobby May, Bobby May, Bobby May, Bobby May.
Keep going.
Bobby
Keep going. One more time. Okay, couldn't hear that one. That is known as sensitivity. So sensitivity is the ability to pick up things that are smaller and smaller and smaller and smaller. So there's selectivity and sensitivity. And when you look at a piece of equipment, something can be very, very sensitive, but not very selective. For instance, if I were to open this filter up really wide, I hear everything, right? I don't really want to hear everything. It might be the most sensitive thing in the world, but it's really annoying to listen to. I could also, however, set it up so that it's really selective. But if it had no ability to listen to anything, that wouldn't be much use either. So there's a lot to be said about setting up equipment, setting up a station. And what happens if you have a lousy antenna? What's going to happen to your sensitivity?
Going to be very poor.
Going to be very poor. That's right. Even if you have a great radio, the antenna is a fundamental part of your station, right? Okay, so here we go. Why are short heavy gauge wires used for DC power connections? This comes back to Ohm's law, because short and thick wires have low resistance. Long and thin wires have high resistance. What does that mean for the case of doing what we're doing? What happens when your wires get long and thin? Your resistance goes up, which means your voltage drop goes up. And if you had a 12-volt battery running stuff and you use up 3 volts in the long, thin wire, how much voltage do you have left to run your equipment?
9.
Just 9.
And it's probably not enough to run the equipment and you won't be able to do it. So in order to maximize the voltage available for your equipment, you want heavy, short wires. Okay, next, which of the following is an appropriate power supply rating for a typical 50-watt FM transceiver? Okay, we're going to do Ohm's law. What's Ohm's law for power? Everybody, P equals
EI.
Yep. Okay. Now, what we're going to do is we're going to say our voltage is 12 volts. It's a 50-watt transmitter. So I is equal to P over E is equal to 50 divided by 12 is equal to 4.3 amps. Is that correct or not? It is correct, right?
Yes.
That's what
Yes.
Ohm's law says. Okay.
Correct.
Now, what would happen if I took a power supply and hooked it up to my radio? That was a 50-watt transmitter. And I hooked it up to an antenna and I keyed the microphone. What would happen to the power supply?
Well, it would put out power.
No, it would not. It would do everything it could, and then your radio would shut off. Because this is
I'm not understanding the question.
if this is a 4.3 amp power supply, like we just calculated,
Oh, well, that's the power supply. Okay,
Yep.
got it. Yes, right.
the power supply would either the power supply would turn off or the radio would just shut off.
Yeah, got it.
Why is that?
Because you're not putting out enough amps to run 50 watts.
Sure you are.
Too
By
much power.
You're
You've gone too much.
assuming 100% efficiency,
Oh,
right?
there we go. We are assuming 100% efficiency. Excellent. Okay. No, we never have 100% efficiency. Okay, so now we start looking at the reality of things. That's why ham radio is ham radio. It's about reality. Okay, so inside that radio, we have something like this. We have transistors. Well, okay, we have to put power in to get power out. Well, what did we determine we needed to do to our signal already? Remember that thing? We had to put DC on it to make this transistor even work. We had to bias our signal. We had to raise it off of the, raise it off the 0 line. We had to turn on our transistor, which means that we actually had to put power in it, even when we're not transmitting anything. We also have all these electronics. And they don't take no power, right? They take some power. And in a lot of cases, just to get the lights to come on in a radio takes about 2 amps. And to put out 50 watts of RF, you need to actually put in about 100 watts of electrical energy. That's about 50% efficiency. So now if we need 100 watts in, we go to Ohm's law again and we find that we need about 8.3 amps plus another 2 amps. Well, that's 10.3 right there. So the nominal rule of thumb is to run a 50-watt transmitter, you need about a 12 amp power supply. So yes.
And that's the 8.3 plus 10 rounded up.
Mm-hmm.
Okay.
Yep. Okay. What signals are used?
Scott, when you run an amplifier with a transmitter, does the amplifier typically have its own power supply then?
Yep.
Okay.
Yeah, and if you have a kilowatt amplifier, it's usually going to be hooked into a 220 volt circuit, like a dryer circuit.
Yeah.
Because to make 1,000 watts, how much power do you need in? To get 1,000 watts out, how much do you have to put in? What do you figure?
2,000.
About 2,000 watts, right? And you can only do at 120 volts, you can only do, a 15 amp circuit will only put out 1800 watts. So either you have a 20 amp circuit or you just have a 220 volt circuit. And that's why when people put in serious shacks at their house, if they're going to build a shack, they have a separate 220 volt supply pulled, because then they can run an amplifier off of it. Okay.
Correct me if I'm wrong, but like cigarette lighter adapters out of a car also pump out that 13.8.
They do, but they're typically only rated, depending on what they are. Used to be they were rated for about 5 amps.
Okay.
And they're not
So
necessarily
then you need to hardwire something.
they're
to the
not
battery.
Yeah, that's exactly right. And that's why like my radio, my mobile radio is hardwired to the battery. With a fuse, of course. With a
Of
fuse.
course.
Of course. What signals are used in a computer radio interface for digital mode? Well, receive audio. You got to get the audio out of the radio and into the computer. Transmit audio. You got to tell the radio what to be transmitting. And you somehow have to have transmitter keying, which switches the radio from receive to transmit. Now, when we talk about computer to radio communications, we have a computer and we have a radio. Right? Normally, this would be hooked up to a microphone with a push to talk button, and you'd have a speaker coming out of it so you could hear what you were listening to, right? Well, okay, except in this case, the computer is going to be doing that job. So the speaker line goes into the microphone input on the computer, and the audio out, which is the speaker essentially for the computer, would be replacing the microphone. Now, you also have to have the functionality of the push to talk button, or PTT. And then that basically is a PTT line. Now, one thing that's really cool about a lot of newer equipment is that you don't actually need these. What you have is a USB cable, and the radio has a sound card in it. And basically the computer then takes over the sound card through the USB cable, and it handles all the functionality by virtue of the software. Makes it a lot easier, a lot less wiring. Okay, how are the transceiver audio input and output connected? That's basically audio input and output of a computer running WSJTX. WSJT is the software that runs FT8. And yes, Sarah, you were right. It was APRS, which I'll put up in a minute. Which of the following connections is made between a computer and a transceiver to use computer software? You have to use the computer line in, goes to the speaker connector of the radio. In other words, the sound coming out of the radio has to go into the line in, which is the microphone input of the computer. If you just draw out the diagram of how to connect stuff, the microphone of one goes to the speaker of the other, and vice versa. Okay, distortion and stuff. Which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? So, very important. What is on a microphone cable when you speak into it? What is really happening? Let's go over and talk about what a microphone is. What is a microphone? Somebody tell me what a microphone is.
Amplifier?
Nope. There may be an amplifier in it, but what is a microphone?
It has a membrane that absorbs your voice vibration.
Yep. And generates what?
It generates some current.
Yep. Generates an electrical signal.
And then the signal and send it to the amplifier, the preamplifier and the amplifier.
Okay. So
Does
because
that make it a transformer?
there may be a transformer in it, but essentially it's a transducer. So how about a speaker? Can a speaker operate as a microphone?
It can.
Actually, it can.
Absolutely.
Yeah, it's just in reverse. So you basically have a membrane connected to a coil that's inside a magnet, and it goes like this, moves back and forth when your sound waves hit it, and it generates It generates wave. It generates an electrical current. Now, because it's moving back and forth, is that AC or DC?
AC.
AC, yes, very good. Okay, so what if you get RF current? Is RF radio frequency AC or DC?
AC.
It's AC. So if you get that on the shield of a microphone cable, it can be carried along the microphone cable in parallel with the signal and actually get back into the audio amplifier that's amplifying your microphone. So a ferrite choke. Okay, everybody here has seen a ferrite choke, even if you don't realize it. A ferrite choke looks like this on your computer power supply. This is a ferrite. What a ferrite does is it is made of largely the same materials as the transformer core, or at least it can be. A ferrite choke is very often a hollow tube where you snake a wire through it. And the point of this tube is that it is important to remember that any wire that is carrying a current will generate what? Nope. Hold your thumb up and roll your fingers over. Any wire generating a current will make what?
Magnetic field.
Magnetic field. Okay. So DC current will make a DC stationary magnetic field. AC current will make a magnetic field that varies at the same frequency. Well, this material right here is a ferromagnetic material, typically iron and cobalt and some other ferromagnetic materials, manganese, and so on and so forth. What it is a bunch of powder, metal powder, oxide powder, bunch of other things, then that are all mixed together with a binder and baked into a shape. So in this particular case, it's a hollow tube. It has a hollow pass through. And this particular combination of materials has a frequency response. And what happens is that at a particular set of frequencies, the magnetic field that is generated by the radio frequency energy in the wire will cause this particular material to respond by entrapping the field and giving it a place to be dissipated in heat, dissipated as heat. Well, if it's dissipated as heat, how much of that RF energy traveling along the wire comes out the other end?
None, it got taken off.
Yep, this is called a choke. And it's made of something called a ferrite bead. These are known as ferrites or ferrite materials, and different ferrite combinations. So iron, nickel, notice they're all metals, manganese, cobalt, the same stuff that you'd often make a magnet out of. These are known as ferromagnetic materials. By selecting the different choices, that changes what the frequency response is right here, which allows you to choke off different frequencies. That could be on an antenna wire. That could be on a microphone cable. I actually have, between my computer and my radio, I have a cable that goes like this, and I have 1, 2, 3, 4, 5 ferrite chokes on the cable. Why do I have 5 ferrite chokes on that cable?
Different materials for.
Nope, all the
different
same. They're all the same.
Because you really don't like magnetic fields.
Because 4 of them was not enough in this particular case. I tried with 4 and it wasn't enough. Every time I transmitted, my computer locked up. So I kept adding ferrites until the problem went away. And I was able to use my computer hooked up to my radio. So that is what ferrites are for. And now we're going to go back to this. Which of the following would you use to cure distorted audio or distorted audio caused by RF current, you would use a ferrite choke. Which of the following connectors is preferred for bonding at RF? Okay, so now this brings up another really important thing, and I'm sorry that we have to go into this much depth, but this is like really important stuff. At least I think it's really important. If I'm
Skin
connecting
effect.
something, what?
In effect.
In effect, yes, skin effect. So if I have a piece of cable that is round and I have another one that is flat that uses the same amount of material, which one gives me more surface area? The flat one or the round one?
Round one.
Well, no, if I have the same amount of material, but I pound it totally flat,
Flat.
the flat one.
The surface.
And we know from yesterday or whenever that was, this thing called the skin effect means that more energy at RF flows right on the outside than in the center. There's virtually nothing in the middle. So if we pound it flat,
The area increased.
you increase your surface area
More
and
surface
you
area,
can
more
have,
electric.
yep, you have more space for the RF energy to flow. So if we're bonding one piece of equipment to another, we typically use a flat strap or a flattened piece of wire or a flat bar for that reason. So which of the following conductors is preferred for bonding at RF? A flat copper strap. Where should the negative power return of a mobile transceiver be connected? At the 12-volt battery chassis ground. Now, anybody ever worked on their car? Probably at some point.
Yeah.
Okay.
Chassis ground.
Yeah,
Back
at
me
the
up.
battery chassis ground. So here's a question. Where in my car do I find ground? Ground is everywhere in my car, right? So here's my very crudely drawn car. I hope I don't own this car.
You gotta skip over all the plastic and all that crap. and
Yeah,
get the
well,
big
but you know,
cable.
like you've got a fender panel and you've got a door panel.
It's still more aerodynamic than a Jeep.
Well, that's true. But okay, so now I have my trunk lid and stuff like that. Every one of these is, you know, every time there's a weld, that weld is ground. So you may notice actually, if you're running let's say you're running a light back here, there's a single wire that runs all the way up to somewhere. And the other connection on that light bulb is just connected to here. It's not, there's only one wire run. Why is that adequate for a light in the car?
Because the whole body is ground.
The whole body is ground. Why is that not adequate for running a transceiver that pulls 22 amps?
Surface is thin.
Well, I mean, it's okay for small loads. It's been designed to handle small loads, but you don't really know what the resistance is between body panels. You didn't pull that wire. You didn't make those connections. You didn't do that welding. So their idea of bonding and grounding is not the same idea as yours. If I have a connection made to a radio that's running over here, I go to the battery.
Directly to the other side of the negative, actually.
Yep. I want to run right to the battery because I don't really want to trust my car body to be finding a route for 22 amps continuously. Finding the ground path through the car. Don't really want to do that.
Is that why they, is
Or
that why they,
grounding to, go ahead.
is
Go ahead,
that why
Bobby.
is that why they suggest when you have a lighter plug in on your radials, not to use it, but to do it right straight to the battery?
Well, the other one is that the lighter adapter is only really designed for 5 amps.
Okay.
Unless it's an accessory plug and they say this is suitable for 20 amp circuits. But the plug itself might only really be, good for 5 amps.
Okay.
All right, so we're saying we're grounding to the battery negative post.
Yep.
Not to where the battery negative
Or
ground.
or if there's a really short wire between the negative post of the battery and the frame of the car, you could go there.
Okay.
Actually, directly to the engine, there is a ground.
Exactly. You could go to the engine ground.
Why wouldn't you just go straight to the positive and negative terminal on the battery?
You
Just the
might
link?
not have enough room. You might not have enough room at the post. Sometimes there's a little cap that goes over the connection. And if
Yeah.
you add something to it, there might not be enough space.
Okay.
How can you determine the length of time that equipment can be powered from a battery? Batteries are given in watt hours or ampere hours. And an ampere hour is an amp times an hour. So if I have a battery that is rated 10 ampere hours, I can run 1 amp for 10 hours, or in theory, 10 amps for 1 hour, or a tenth of an amp for 100 hours. So basically an ampere hour is a rating of the capacity of the battery. So if I have a battery that's rated, let's say 30 ampere hours, that's amp times hour, and my radio draws 3 amps, how long am I good for?
10 hours.
10 hours. If I have a radio that draws 1 amp, how long am I good for?
30.
30 hours.
Well, that's assuming that your battery is strong and stable and holds its charge, et cetera, right?
Exactly. Okay. Operating controls. Here we go. Operating control. What's the effect of excessive microphone gain on single sideband? If you over modulate, you will basically drive your amplifier into a place where it's not linear anymore, and it will sound like this. So if you have too much gain, you're basically driving it past the ability to be linear, and your voice will sound distorted. If you're tuning an FM receiver above or below
Scott,
yes,
just a second. So on single sideband, you want less microphone gain than on FM?
no, you want appropriate microphone gain.
Okay. So my microphone gain when I'm on 2 meters is my radio sets it at 50. And
Yep.
when I'm on single sideband, it's like 32.
Well, you can adjust it based on, what you think you need.
Well, the only way I would know what it thinks it needs is what the person on the other end is hearing, right?
Depending on the radio you have, you might actually be able to listen to yourself.
Okay.
One cool thing about having web SDRs out there is that there is one of them, which is in Utah. And from here in Oregon on 40 meters, if I transmit, I can hear myself. I can actually listen to my own transmitted signal and listen to what it sounds like. A lot of radios also have a monitor circuit, like a studio monitor. You can listen to yourself.
Okay.
Built into the radio through headphones. If you tune an FM receiver above or below a signal's frequency, it will sound distorted. How do you enter a transceiver's operating frequency? You have a knob. Sometimes you also have a keypad. You can enter directly. Every radio's got a keypad. A way to enter a favorite frequency or channel, you store it in a memory channel. That's how a lot of us use repeaters. We have a repeater programmed into a memory. Scanning function of an FM transceiver is to scan through a range of frequencies or scan through a bunch of memories really, really fast. Whenever I'm not using my radio, I just leave it scanning all the frequencies that I would normally listen to. If I hear something pop through, that means that somebody's busy. Maybe I'm interested, maybe I'm not. The purpose of a squelch function. Okay, so let me see if I still have my web SDR open. Okay, can everybody see the web SDR?
Mm-hmm.
Yep.
Okay, so let's say I go here and I hear nothing. Squelch basically would allow me to do this. If there's no signal of interest to listen to, the squelch would basically knock it down. Okay, next one. How is squelch adjusted so that a weak FM signal can be heard? You typically would open up the squelch all the way. We do a simplex net here on the weekends. And we tell everybody, because above a certain
You're still
threshold, you'll
on the
hear
other
something.
website.
Oh, sorry about that. How is squelch adjusted so that a weak signal can be heard on FM? You adjust the squelch so that it's open and noisy. That way you can hear the weak stuff. Because with FM in particular, if there's no signal there, you'll hear just noise. And if there's a weak signal there and you have the squelch turned on, you won't hear it at all. Repeater offset. Okay, offset is basically the same thing as operating split. So if I operate split, here's my transmit frequency, and here's my receive frequency. And this might be 7.002, and this might be 7.004 megahertz. So why would I want to do that? Well, if there's somebody on the other side that is receiving on 7.002 and someone on the other side who's transmitting at 7.004, then we can, use two different frequencies. We still can't really talk at the same time unless we have separate receivers and transmitters. But the benefit of doing that is that, let's say that there is another station that's trying to contact me also, that is right here, and another one that's 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 here. This is called a pile up, where a whole bunch of people are trying to talk to you at once. Now, if they were transmitting on the same frequency that you were transmitting on, then nobody else in the world could hear you because they'd be just swamping you. And how would you control anything if nobody could hear what you were saying? And the answer is you couldn't. So the benefit of doing this is that as the receiving station, you can listen in to this whole range of frequencies and say, oh, I got this one, and I'm going to pick that frequency, and I'm going to tell all the stations that I heard station A. And then everybody else can shut up and let station A make the contact. And then you say, okay, well, I'm listening again for everybody else. Now station A is gone because they don't need to be there. And now say, okay, well, I'm listening for somebody else. And now you hear station B. And you say, okay, well, I'm now tuned to station B. Station B, go ahead. And this is known as split operation. That would be split when listening and receiving on different frequencies. Now, there's another reason why we would use a split operation. A repeater is basically a box on a mountaintop. And connected to this box is an antenna. So this is a repeater on top of a mountain. Now, a repeater, unlike me, has a very interesting way of operating. It listens on one frequency for people everywhere. And at the same time, that receiver that's built into the repeater is putting information, the same information, out to a separate antenna on a different frequency and simultaneously retransmitting it to everyone.
And that's the so-called offset.
The difference in frequency between the receiver and the transmitter is known as the offset. The reason that a repeater works this way is that it allows people to hear each other in real time. So the difference in transmit versus receive frequency, in the case of our club repeater, let's say it's 146.72 megahertz, and its receive frequency is 146.12 megahertz. That offset is 0.60 megahertz. When you on the ground are listening, you are listening on 146.72 megahertz. When you transmit, you want to be heard by the repeater, which means you are listening on 146.72 and you're transmitting on 146.12 megahertz. When you set the repeater offset in your radio, it will automatically, when you key the radio, switch frequencies based on what you have programmed in as the offset. The direction has to be right also. So this is known as a negative offset, because your transmit frequency is below your receive frequency. Depending on the repeater that you're on, it could also be a positive offset.
So I have a quick question. That's something I deal with. That's what we do. That
Yep.
Our radios, our repeater sets, the whole bit. Is it not as common in amateur radio? Is it more, propagation and skipping signals, or
is which part of it?
The repeater part. So are there less repeaters and more like bouncing signals off the sky and stuff like that, or is it both?
Oh, it's both. I mean,
okay.
Like here's Oregon. Let's see, region.
Aren't the repeaters more on the 2-meter scale and not so much on the HF bands?
Yeah, there are very few repeaters on the HF bands because FM takes up a lot of space. Okay, so I'm going to share ORRC. Okay, these are the repeaters that are coordinated in the state of Oregon.
It was quite a bit.
There's a lot. Yeah.
Yeah.
And the reason that we have a coordinator is because there's, a limited number of frequency pairs that are available. And for instance, 146.72 is the Valley Club's repeater. Notice that we actually share this frequency with another repeater in Astoria. So we're in Junction City and the other one's in Astoria. And we have the ability, in theory, to basically wipe each other out. Look, there I am as the trustee. So basically, in order to make sure that we don't interfere with each other, somebody has gone through, and this is a volunteer organization, ORRC, that has been picked with people picked to coordinate frequency pairs to avoid interference.
My agency, we have several frequencies, and I'm the trustee of the frequencies through the FCC, yada, 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 all that stuff. I use repeater book and stuff like that to, and we have an in-house guy that programs our stuff for us. He showed me some stuff, but he's not a ham guy. So it's a couple different worlds clashing here right now.
He's not a ham guy yet.
Yeah.
Work on him. You work on him.
I am.
So Scott, is the way that Astoria and Prairie Peak don't interfere with each other is they use different CTTS tones?
They can use different CTCSS tones, and it could also be that there's enough mountains in between that there's, that they're just regionally separated.
Okay.
By terrain.
Is there a range on a repeater for those of us out here in the flatlands? We don't have a mountain to break it up.
Depends how high it is. I mean, if you think about it, if you're in an airplane at 40,000 feet, your horizon is 250 miles in all directions, right?
Okay.
So, like we put up an APRS, we put up an APRS balloon that works on 2 meters. It was floating around at 40,000 feet and getting picked up. It was transmitting 10 milliwatts and getting picked up by stations 200 miles away.
We're actually working on a project.
Fun. Okay, so here in the flatlands, if I put up a tower 50 feet, 100 feet above the cornfield, and somebody down in Peoria puts up 100 feet above his cornfield, are the two repeaters going to collide, or is it a matter?
Don't know. You gotta figure out how far you are and whether or not your coverage patterns will interfere.
That's what I'm at. Is there a standardized range for repeaters, or is that depend on how much?
It's based on terrain. It's based on terrain. Like somebody had said something about bliss pack radios. And you go but get a blister pack radio and it says range of 45 miles. Well, yeah, if you're standing on Mount Everest.
Yeah, that was me.
Yeah.
And buying $80 radios and expecting them to go more than 2 miles and being very disappointed.
Well, yeah.
Now, one thing I've looked into with repeaters is a lot of it is just like your modem. It's going to depend on how much power it's putting out. It's going to depend on its antenna.
Yep.
And not all repeaters are the same. And
Yep.
I've got my son up in Iowa right now serving a mission for the church, and it is so flat that I look at pictures he sends back and I drool. I'm like, man, my signal could go forever up there.
Yeah.
You
So
said
here,
he's in Iowa?
Yes, sir.
Where in Iowa?
Hold on. I had it. He's doing Illinois and Iowa, and
Right.
I'm
He's in
pulling
Iowa
up the
City
map.
Mission.
Yes, Iowa City Mission. And where is he right now? He's in Illinois right now. He was in Des Moines for a little while. Pontiac. That's where it is. He's in Pontiac.
Pontiac, Illinois? Okay.
Yeah.
I know where that's at.
okay.
All
So
right.
now what I'm
That's
going to,
my sidebar.
okay, what I'm going to bring up here is, let's say I have a 1 watt handheld radio, and I hook it up to an antenna that I have carried along in my car that is 40 feet above the ground and has 10 dB of gain. All right. So what does the 10 dB look like? How many times? 10
10
times. So I'll have the equivalent of 10 watts of forward power going out in the forward direction. And how high is the antenna?
40 feet.
40 feet. Okay, well, that increases my range considerably, right? Compared to, let's say, 5 watts with a handheld antenna. Which one's going to do better? So,
40 feet beats handheld every day.
well, yeah, right. So that's why people go to high places to do things. That's why mountain topping is a lot of fun. If I were to go to, okay, so I've got to go to APRS, and the other one I have to show you guys at the next break is going to be Radio Mobile Online, which will give you a little bit better understanding of what we're trying to do. Okay, back to this. Okay, that's repeater offset. What function is performed with a transceiver and a digital mode hotspot? That's communication using digital voice or data systems over the internet. So there's a lot of integration between ham radio and the internet. We do something called Echolink. We do something called IRLP, Internet Radio Linking Protocol. These allow us to take internet-based things and combine them with radio-based things, which basically means that if I'm traveling in Europe, I want to check into my local repeater, I can open up Echolink on the app on my phone, and I can connect to my local repeater over the internet, and then have a signal that's coming out in RF. So people who are riding around town can have a conversation with me. What is a talk group on a digital repeater? Is a way to share a channel at different times without hearing other users. The interesting thing is that a digital repeater, because it's digital, that can actually be connected to the internet, and 2 repeaters very far away from each other can be connected to each other. So your talk group might be a bunch of people in Oregon and a bunch of people in Illinois, and they're connected over the internet using the Internet Radio Linking Protocol or voice over internet. DMR code plug, you'll hear this code plug thing. Basically, that is a program for programming your radio so that you have repeaters and talk groups programmed into the radio. And DMR again stands for digital mobile radio. Specific groups of stations are selected on a digital voice transceiver by entering the group's ID code. So if you have the wrong ID code programmed in, you won't hear the group that you expect to hear. The color code of a DMR system establishes groups of users on that DMR repeater. D-Star is a special type of digital mobile radio. It's ICOM and Kenwood that have come up with it. And your radio has to be programmed with your call sign, because your call sign is actually sent as digital information when you transmit.
Is that like the packet?
It is kind of like a hybrid. It's not packet because packet is sent analog. It's sent over FM, and it kind of it's a different protocol.
Okay.
Yeah, DMR and D-Star are different protocols than packet. They're all
Okay, thank you.
forms of digital.
Okay.
The advantage of having multiple receive bandwidth choices on a multi-mode transceiver, we just experienced that. You know, if you want to filter out other things, you can reduce the noise by selecting an appropriate bandwidth. So for Morse code, it's 500 hertz. For single sideband, it's like 2,400 hertz. And that's based on the approximate bandwidth of the signal that you're listening to. So something called an RIT or clarifier, that is basically invoking sort of like a split frequency. It allows you to change your receive frequency without changing your transmit frequency. So you could operate split. You could also operate with the RIT turned on, and that would allow you to account for slight variations in frequency of another signal. What is the PTT button? That is push to talk. Yep. When you do that, a signal is grounded, which forces the transmitter into the transmit mode. Okay, a transceiver is a portmanteau of transmitter and receiver. They're mushed together into a new word. Combines transmitter and receiver. Another device is called a transverter, which is a transmitter converter. Now, the way this works is, let's say I have a transmitter that's operating on 28 megahertz. And I have this device. Does anybody remember what that big X in a circle is called?
Mixer.
That's a mixer. It adds and subtracts frequencies together. And let's say I combine this with 194 megahertz. I will get sums and differences of those. So I will get 222, and I will also get 194. I'll get the original stuff, and 28. And I'll also get the difference, which is, let's see, 166. And I'll get 2 times each one. So I'll get a 56, and I'll get 388. And basically there's a whole mess of stuff that comes out of there. Well, it turns out that 222 megahertz is a ham band. It's 1.25 meters. And there's not a lot of equipment available, but we're allowed to use the band. So if I were to take this and mix those two frequencies together, I would get the target one, which was 222, and I'd get a few things down here and some up here and here and here, and maybe one down there and another one up there. And this is the target frequency, 222, that I want. What would I do to make that work? How do I get rid of all the other ones?
Wait a minute,
I would build a filter.
back me up here. The mixer is taking a 28 megahertz signal.
Yep.
A 194 megahertz signal, and it's putting them together.
Yep.
And making that into a 222 signal.
It does sums and differences. Well, it does 222, but it does all kinds of other stuff too. Mixers are really messy.
Well, where does the 166 and the 56 and the 388 come from?
Well, what's 194 minus 28? Because it does
166.
sums and differences. So 398 or 388, that's 2 times 194 is 388. 2 times 28 is 56. So you have to get rid of all those frequencies.
Sounds like an out of control 3-year-old with a calculator in his hand.
Yes, it does. Well, okay. So now we've used filters to take care of this and generate another frequency on another band. That's known as the function of a transverter. Interestingly, do you think we could take 222 and run this backwards?
Why not? If we can combine things, we can surely split them. There has to be a divider machine.
Yep. It works in both directions. If I take 222 and mix it with 194, I get my 28 back. So I can just turn it around. And of course, I still have to do filtering on this because now I want 28 and ignore all the other ones. So this is a two-way device. This is, again, known as a transverter.
Transverter.
And the key part of a transverter is that thing known as a mixer. That allows us to convert one frequency into another. This is also known as a local oscillator.
The transverter is called the local oscillator?
Nope, the thing that we put in, that we have chosen, the 194 megahertz. That's a local, that's generated by something called a local oscillator. Because this is the thing that we have control over. This is something that we make in the radio, and this is out in the real world. The 222. This is the thing, the local oscillator that we can control. This is how a beat frequency oscillator works in order to generate audio. By controlling the local oscillator frequency, we can do all kinds of cool stuff.
Are we not also controlling the 28?
We are, but how about if it's coming in this way? Coming in from the outside world. We get out what we get out, right? You get what you get based on where you tune. You can't control what's coming in from the world. You can control what's, again, like you said, you can control what's being generated here. That controls what comes out. You can't control what comes in and what comes in.
Okay, so the 28 is ambient somewhere on Earth and the 220.
Well, no, the 28 is inside your equipment. The 28 megahertz is inside your equipment.
But I don't have control over it. I only have control over the button where the 194 is hiding.
Yep. Well, in this particular device, this might be, this is another radio.
Oh.
And this is an antenna. This allows us to basically use a radio on a band it was never designed for.
That sounds totally geeky and makes perfect sense in this class.
Yep. And in fact, that is one of the many things that we do. And in fact, for instance, darn it. Microwave. Down east microwave. DEM makes some really good transverters. They've been in business for a really long time. Here, low level transverter, only $300. You don't have to build it yourself, but you can. Okay, what device increases transmitted power output from a transceiver? That would be an RF power amplifier. What is the function of the single sideband / CW FM switch on a VHF power amplifier? Notice it says set the amplifier for proper operation in the selected mode. Okay, so what is at the center? What is the central device inside an amplifier today?
It'd have to be a transformer.
No, close. What is the power amplifying device inside an amplifier? We talked a transistor, right? What do we know about a transistor in order to function and do its job? What do we have to do? We have to raise the voltage of the input and output signals, right? We have to raise the voltage of the input signal and lower the voltage of the output signal by a DC offset in order to get it to work. The SSB CW FM switch, Morse code is either on or off. FM is just the presence of a frequency. We don't really care whether or not the transistor is operating linearly when we're using CW or FM. How about if we're doing single sideband and we have distorted audio coming out? What's that going to sound like?
Garble.
Garble, that's right. In other words, why bother doing it? So there's a switch that allows you to switch the mode, which changes the biasing on the transistor so that it works properly for the selected mode. Which term describes the ability of a receiver to detect the presence of a signal? Sensitivity, just like your hearing. To discriminate between multiple signals is known as selectivity, the ability to pick one instead of the other. Where is an RF preamplifier installed? Okay, this is another drawing map kind of thing. So let's have an antenna up here, and we're going to have a signal coming in to the antenna, and then we have cable, and we have 10 dB of loss in the cable. Let's say it's a really high frequency. And we are going to have a receiver that has a sensitivity of minus 120 dBm. dBm means with respect to a milliwatt. A milliwatt is already 0.001 watts. What is minus 120 dB? It's 1/10, 12 times. So the amount of power that this receiver can actually hear and make sense of is 0.0000000000001 watt. This is real. This is why we use decibels. You see all those zeros? This receiver, because of the amplifiers inside it, can actually hear a signal that is only that much power and do something with it. But let's say that the antenna, because it's not very good at what it's doing, because it's an antenna, it's just picking up noise from the atmosphere, right? Has a signal, a received signal coming in of minus 115 dBm. So if this was perfect cable and that signal made it all the way in, would we be able to hear the signal? Yes or no?
Yes.
Yes.
Yes. But now let's replace this cable and say that it's getting old and lossy and it's just real. How much signal makes it down to the point down at the bottom?
None.
Minus 125. Okay. So do we hear the signal now?
No.
Wait a minute, where did the minus 125 come from?
Minus 115. And then another minus 10. We have lossy cable.
The minus 10 is added to that?
That's right, because signal has to go through the cable.
It wouldn't just die out in the cable?
It would. Well, no, there would still be something there, but it's minus 125. The question is, can our receiver with this sensitivity hear it?
No.
It can't. So what if we took a signal? What if we took a little box that was a preamplifier right here that had a gain of plus 10 dB with a sensitivity of minus 120 dBm? Would that help?
Yes.
Nope.
Plus
Why?
10 and minus 10 wash each other out, so now you got a clear signal.
Nope. Because how much? Because this is the sensitivity minus 20 of the preamplifier that we just put
Oh,
in.
it's still too low.
It's still too low. But we could do something to make this situation better. What we can do is we can take the preamp and put it way up here. We can add a 10 dB right here. And now what do we have right here at the output with the little star? We have minus 115 plus 10. What is that?
0.
105.
Minus 105. We have minus 105 dBm. Now, when we get down to the bottom, we have minus 105, minus 10, and we get
minus 115.
Minus 15.
And what do we hear?
All of it.
We hear it all. So by selecting where our preamplifier goes, that can determine whether or not it actually works. So if we have a received preamplifier, we want to put it up as close to the antenna as possible. And if you're building a station that is listening for signals coming off of the moon, for instance, which are really, really, really weak, you actually typically put a preamplifier all the way up at the antenna. Now, what's the problem with doing that?
Climbing up the tower to where the antenna is?
Let's say you put it up at the same time as the antenna. So that's not an issue. But what is the issue? Where is the preamplifier?
It's before the wire, and you're going to have continual degradation.
Yeah. Okay. What else about it?
You need power.
Yep, you need power. And what else about it? It's in a box.
Rain,
Rain. It's got to be waterproof. It's got to be, you know, designed to get cold. When it gets cold outside, it's got to be designed to handle heat. All the connectors have to be waterproofed. And you got to get, like you said, you got to get power up to it because it doesn't work on nothing. So basically that tower mounted preamplifier is an active device and it needs to be taken care of because you don't want it to fail. So there are special considerations when putting one up.
We used to add in the TV antennas, the little plastic box amplifier.
Yep. And actually cable systems do it too. To boost the signal before it gets down to your house.
Yeah, that's right.
Which of the following is used to convert a signal from one frequency to another? Everyone?
Mixer.
There's the mixer. Okay. The name of a circuit that generates a specific frequency
Oscillator.
is known as an oscillator. What the function of combining speech with an RF carrier?
Modulator.
Modulation. And how about taking it back out?
Demodulation.
Demodulation. Okay, very good. Okay, which of the following causes radio frequency interference? Fundamental overload. That means that there's just too big of a signal nearby. It wipes everything out. A harmonic is a multiple of a frequency. So if I have a fundamental frequency that I'm transmitting at 10 megahertz, my next harmonic would be at, these are integer multiples. So where would my next harmonic be? I'd have my fundamental at 10. My next one would be at
20.
20. And then there'd be another one at
30,
and another one
40, 50.
and so on and so on and so on. So here's my fundamental at 10 megahertz. I'd also have one at 20 and one at 30 and one at 40. And by the FCC rules, if you're building a transmitter, we are allowed to build our own transmitters. All harmonics must be, depending on the frequency you're on, either 50 dB or 60 dB less than the fundamental, than the design transmitter frequency. This is why we go through class, because all harmonics and then all spurious emissions, which are just randomly generated signals, this feeds into something called spectral purity. When you buy a device, it's already been checked for spectral purity by its designers. But because we are just given the green light, carte blanche to design our own transmitters, part of that is an understanding that all output coming out of the transmitter has to be, if it's not on the fundamental frequency, a certain number of decibels below the fundamental. And how do we achieve that? What do we build?
Oscilloscope?
Nope. We build that. We build filters. That's right. We build filters that have something called ultimate rejection in dB outside the passband. And compared to the initial passband, they have insertion loss. And they also have this. They have a bandwidth that is defined by the 3 dB bandwidth. So when we build filters, those are all things that we need to take care of. You basically pick your components, and most of your components are what? Capacitors and
Inductors.
And you pick your components. You can have multiple ones. You could have something that looks like this. You can actually build a filter that looks like that. And by picking your different values of your inductors, that would determine what your band pass looks like. Pretty cool. I know, pretty cool. And it's all defined by mathematics. So fortunately, You don't have to go and do the math yourself. If you have a design frequency and a design impedance, there are actually tables out there and websites that have basically got calculators on them that allow you to plug those things in, and they'll give you your component values. But let's say that you have a filter that you say, okay, this is going to work, and it says that you need 2 times 7.8 millihenry inductors, and you need 3 22 picofarad capacitors. Well, those you can probably buy. How about a 7.8 millihenry inductor? Maybe you can, and maybe you can't. So if you can buy it, you can buy it. How else could you, what can you do if you can't buy it?
Make your own.
Make your own. Yep. You go like this, you grab a piece of wire and you figure out how long it has to be and what the diameter has to be, and you wrap it around like a pencil or something, and you just start winding it until you're done. And then you solder it in place. It's a really cool way to learn how things work.
And we all do that in our basement 3 times a week.
No, but I have, well, and also, you know, that what you find out is that if your frequency is not right, you can give it a little squeeze, and that changes the inductance, and that changes how it behaves. That changes the resonant frequency.
It might be kind of fun to be that much of a geek.
It is. I tell you what, it actually is. And the thing is that we are allowed to do this stuff. You know, we're encouraged to do this stuff. Which of the following actions can you take if your neighbor tells you that your stations are interfering with their radio or TV? Okay, so there's a part of the FCC rules called Part 15. Part 15 covers unlicensed and it covers unlicensed receivers and transmitters of energy. Basically saying they're incidental receivers and transmitters. In other words, they're not required by any other rules to be like the stuff that we do. Commercial radios are typically Part 97. Family radio service and GMRS, those are covered by Part 95. CB is covered by Part 95. Amateur radio is covered by Part 97. Part 15 is basically everything else. So your phone, that's typically going to be Part 15. The Wi-Fi router is Part 15. Now they still have to meet some they'll actually have a stamp that says FCC or something like that. My power supply that plugs into my computer is Part 15. So what if I am transmitting with a kilowatt and my computer power supply decides that it's going to start, you know, basically not powering my computer anymore while I'm transmitting? Whose fault is that? What do you think, everybody?
It's your fault.
Nope.
Yours.
Nope.
No, it's the manufacturer because they got it certified.
That's right. The manufacturer, because it's the manufacturer and the owner of that Part 15 device, because who has the license to transmit at 1500 watts?
You do.
That would be me. I have a license. That computer power supply must accept all interference, right? All radio frequency interference from licensed services, and must not interfere with any other licensed services. So if I have a neighbor who bought a grow lamp because they're growing pot in their basement, which is legal in Oregon, by the way, and they put in a couple of grow lights in their basement, and they are interfering with my ham radio, the fact that I can't receive certain frequencies, whose fault is that?
It's
their fault. That's right. It goes back to them because they bought it, and the manufacturer because they built something that was RF noisy. And the FCC actually cares about these things. RF noise generation is actually a really big problem. So if you are interfering with your neighbor's TV or radio, okay, well, you go over and make sure that everything at your station's working properly and that it doesn't cause interference to your own radio. Beyond that, you can help them. You don't necessarily have to help them. You might just tell them, look, your radio is a piece of crap. You know, you need to get a new TV. It might also be that you could help them by trying to install some filtering on their radio or TV or wired telephone or whatever it happens to be.
So,
yes.
so stop my desk lamp that turns on and off my APRS radio
Mhm.
that says this device complies with part 15 of the FCC rules.
Yep.
That's a lie.
Well, it does, but it does. But the question is, if you end up in a situation where you're transmitting and your lamp turns off, right? Well, you just found a place that, okay, well, you just found a place where it doesn't. Although it really does, right? It really does, because it has to accept all forms of interference and it has to not interfere with any others.
Okay.
So if you find a situation where it does interfere, well, okay, then it's not really complying. And
So
but it does have to accept
that.
A ferrite could fix that.
Yeah.
It could also be a fundamental design flaw, in which case it's a bigger problem.
Right. Okay. Thanks.
What should be the first step to resolve non-fiber optic cable TV interference? That would be sure that all the connectors are tight. If the connectors are not tight, essentially they leak. They leak going out and they leak going in. If they leak going out, they can interfere with you. If they leak going in, they can pick up signals that you are transmitting and you can wipe out your TV signals. Broadcast AM or FM receiver, why would it receive an amateur radio transmission or other unintentionally? Basically, you have a receiver that's unable to reject strong signals outside the band. Now, I've also had this happen where I was listening on my ham radio and I was driving by an AM radio transmitter and I could hear it on my ham radio. Well, because it was, let's say the output on that frequency that I was listening to was at least 60 decibels less, but it's a 10,000 watt transmitter. 60 decibels is a million times. A millionth of 10,000 is still 100th of a watt, and I'm driving right past the transmitter. So it's 100th of a watt at a distance of 100 feet. I could still hear it. Fundamental overload of a non-amateur radio or TV receiver. Okay, so fundamental overload means that basically the receiver's amplifier is just getting swamped and it's amplifying everything that's coming down the antenna. Fundamental overload basically just means that there's so much coming down that it can't differentiate between things that it's supposed to hear and things that it's not supposed to hear, and it's just amplifying everything. So if you install a filter to block the other signals that it's not supposed to be hearing before they go down the antenna into the receiver, then there's a chance that essentially the receiver will now work properly. What can reduce overload of a VHF transceiver by a nearby FM station? Installing a band reject filter. Okay, so we had a band pass filter. A band pass filter has this shape where it passes these frequencies. A band reject filter is upside down, where it passes the upper and lower frequencies and blocks these. And if this is FM 88 to 108, then essentially you will block FM radio from getting into your transmitter and receiver, which is generally a good thing. Most of us don't need to do this, but depending on how close you live to an FM radio station, you might. If something in your neighbor's home is causing interference to your station, you have the license. The first thing you're going to do is make sure that everything in your station is okay. The next thing you're going to do is work with your neighbor to identify the device, and you're going to inform your neighbor that the rules prohibit the use of devices if you can't figure it out. If your audio signal through an FM repeater is distorted or unintelligible, your batteries are running low, that means your reactance modulator is not doing what it should be doing, and it doesn't have enough voltage to function properly. And if your transmitter is off frequency, if you're in a bad spot, the bulk of your signal is not getting to where it needs to be going. And you might sound like that again. RF feedback, basically RF feedback in a transceiver ends up sounding garbled. It does the same thing as over-modulating, over-deviating. Basically, too much signal or too much voice or RF feedback in a transceiver, the end result is that it sounds garbled. Okay, most handheld radios do not have a microphone gain control. Since they don't have a microphone gain control, how do you get less signal into the microphone? You simply move it further away. If someone tells you that your signal is weak, your audio is not deviating properly, you move it closer and then you talk louder. Okay, we're up to basic test instruments and soldering. Okay, so basic test instruments, we're going to draw a meter on a circuit. So here's our circuit. There's our circuit. Okay, we want to measure a voltage, the voltage of the battery. We would go like this. We would put it in parallel with the thing that we're measuring. We get a plus and a minus, and we would measure the voltage. Now, we wanted to measure, let's say we want to measure the current. We would do this. We'd break our circuit right here and install a meter, which is basically, it's going to have a deflection of a pointer that's going to show us how much current is flowing. How about if we want to test the resistance of this resistor? Can we do this while the thing is connected?
Sure.
Actually, we can't. Actually, we can't. And the reason is that if we want to measure resistance, we go like this. We have an ohm meter. And by Ohm's law, what's Ohm's law, everybody?
Hi.
E equals
I times R.
I times R, right? Okay, well, we don't know R. R is equal to E divided by I. Well, okay, well, what do we already have if we have this connected to a circuit? There's already current flowing. There's already there's already a voltage. Now, you could measure those two things and know what it is, but if you have an ohm meter, that doesn't really work. So in order to do that, what you would do is you would break your circuit, like right here, disconnect it so that there was no completed circuit. Because inside an ohm meter, you basically have, I'm going to replace the ohm meter. You have this. So what do you see right there? What are the two things?
Capacitor and a battery?
Yep. You have, well, no, you have a battery and then you have this A up here.
What is that?
That's an ammeter.
Oh, okay.
Current measurement meter. And then you also have a voltmeter right here. So what is this what is this thing doing? It's applying a voltage through the circuit, which is causing a current to flow through the circuit. This resistance is unknown. And by doing Ohm's law, what can it tell you?
What the resistance is.
Tells you what the resistance is. The resistance is the unknown. It applies a voltage, measures the voltage, measures the current, and tells you what the resistance is. So now let's replace this resistor with a capacitor. Well, okay, now that we know what's actually inside our ohm meter, what's going to happen in this particular case?
Will absorb the energy.
What's going to happen? The capacitor is going to start by absorbing all the electrons and charges, and then it's going to charge up, and then what happens?
Zero resistance.
Zero. Well, no, zero flow. Right? At first,
Yeah,
you're going to have
yeah.
zero resistance, but then once the capacitor is fully charged up, there's no more current flow, and the resistance is going to look like infinity. So if you look at it over time, what you would see is here's your resistance. It would start at zero and then go up to infinity. So if you see a resistance that starts at 0 and then goes up to infinity, and it actually shows infinity, that means that there's a capacitor in the circuit that you're charging up. That's what that means. Okay, what would you use to measure electric potential? Potential is electromotive force. They're the same thing. That's a voltmeter. How would a voltmeter be connected to apply to measure voltage? That would be in parallel. How can you damage a multimeter? Well, considering that the resistance setting is an ohm meter and it has a battery in it already, as well as an ammeter, by connecting it to a circuit that is already connected to something, or trying to measure voltage when you accidentally have it on the resistance setting, you've now taking, let's say, 120 volts and running it through your ammeter in your meter, or you're backfeeding your battery. Having done this before, I'm very happy that my ammeter, that my multimeter has a fuse in it. So it protects your multimeter from blowing up. I've done that more than once. Which of the following precautions should be taken when measuring high voltages? So what we're going to do really quick is we're going to look at this website. Has anybody ever been here?
Nope.
You've never been to Harbor Freight? You've never,
No.
not lucky enough to, has anyone ever been to Harbor Freight?
Yeah.
Yes.
Harbor Freight is a great place to get adequate tools for a lot of jobs, right? Look, there's all kinds of stuff that's almost free. I'll bet they even have a multimeter for almost nothing. And let's see, multimeter.
A few years ago, they were giving away for free if you
I
showed up.
know. Yeah, I've still got one. Oh, look, 7-function digital multimeter, $6. Ooh, and it was 7. All right. So now, even here, notice you've got a multimeter that's $100. Here's one that's 75, and here's one that's 20. Now, I could also go and get one of these. Notice the price on this. $469 and worth every penny. I have one of them at work.
Yep.
What's the
I have a
difference?
system too.
What's the difference even beyond accuracy? What's the difference?
Reliability.
Yep. What else?
How easy it is to destroy.
Yeah, well, yes. The fact that the cheap one, it has leads that are rated for probably, 120 volts. These meters are rated for 1,000 volts. And, they're almost indestructible. So that is the fundamental difference between one meter and another meter. Certain things I would test 1,000 volts with. That cheap meter is definitely not one of them. How is an ohm meter connected for a component to measure its resistance? You connect it in parallel because it has a voltage source and an ammeter in it, and ensure that the circuit is not powered. And ideally, your component is disconnected when measuring an in-circuit resistance. If you have a large capacitor, your resistance increases with time. Instrument used to measure electric current. Electric current is measured in amps. So an amp meter gets shortened to an ammeter. To measure current, unless you have an inductive ammeter, an inductive ammeter clamps onto the wire, but most people don't do that because they have a limited range. They usually require many amps to work. You would connect an ammeter in series with the circuit. Two kinds of soldering. Notice we have acid core, lead, tin, rosin core, and tin copper. Which one should not be used for radio and electronics? Acid core is for plumbing. Do not use it for electronics. Mostly we use tin and lead with a rosin core. Finally, the characteristic appearance of a cold tin lead solder joint is that it's rough or lumpy. Basically, when you're soldering two wires together or soldering something to a circuit board, the solder makes a mechanical connection as well as an electrical connection. It looks like it flows properly to both things that you're soldering, because it actually does. It fills the gap and also makes a good solid electrical connection. All right, how about a 5-minute break, everybody?
Sounds good to me.
Okay,
Have we had lunch? Did I miss it?
lunch? I didn't
Yeah.
have lunch. It's only 11 o'clock in the morning here.
It's 2 o'clock here.
Yeah,
I get lunch when it's over
yeah.
at 3.
I'll be lucky if I get, no, I'll get one.
So Scott, I mentioned in the chat that you might want to publish the ferrite
Yes, yes, I'm
website
actually
as
doing
well
that
as the
right now.
APRS one.
Yes, I'm actually doing that right now. So here's, I'm also going to pull up the website for that. And then I'm going to use the bathroom.
All right. See you in 5.
I'll see you, well, less than 5 now.
Where did that thing go that you just had up? It disappeared off the screen.
What's this one?
Something about ferrite?
I sent it. If you click on the chat button, it's in the chat.
Chat. Okay, got it. Thanks.
And here's what the ferrite looks like. These are frequency response based on selection of materials. And here is APRS.
Well, Scott, what are we looking at here when you say we're looking at APRS? What are we seeing? He's gone.
These are people that are registered, and so it's showing what their call sign is and what their last location was.
Okay, so this is geographically tracing people who are going different places or in various locations.
Yeah, people who are using the app.
Okay. So if I want somebody to track me, I would use APRS then.
Yeah, you would have to be set up so they could read it, but if you had it set up, they could see you constantly.
I see. I have a friend who's a hiker. He has like a spot locator thing. And you can tell where he's at. I must use APRS.
Yeah, that or a similar technology. One of the other things that's used for, not used called APRS, but you can do low jacking on your fleet vehicles. And that way the boss can always see where your vehicle is.
Right.
For a little bit, they were using that with UPS and FedEx, so you could actually track where the truck was. And that led to some issues, so they backed off real-time tracking.
Right. Thanks, Jared. Appreciate those answers.
Hey, no problem.
All right, everybody ready to go again? I don't know if everybody's back yet.
I was born ready.
Okay.
Okay.
Okie doke. So what we're looking at is APRS, which is the Automated Packet Reporting System. And it's APRS.FI. And this allows you to track on a map. This is based out of Finland. Individual stations, notice all the weather stations. Oh, here's a track down below. Notice the green track. We can click on the dot, W7SEA, 70 miles an hour at a certain time. And every one of these where there's a dot is a beacon of information that was sent out. So here's one, here's another one. So I'm not sure where they started. It looks like up by Portland. There's a dot. So this is useful for recording information, or like Sarah was saying, figuring out where somebody is and when, because it's basically a GPS combined with ham radio put on a map. The other one is ferrite, which Sarah mentioned. Notice that we now have suppression materials, inductive materials, and power materials. These are all, notice, different mix types. They're given numbers. Suppressing materials, type 43 is very common. Type 31 is very common. MnZn, so that's manganese and zinc in some combination. Notice we have flux density, that's magnetic flux. Permeability, that's the impact, that's the effect that it has when a magnetic field is applied. And notice, most importantly, recommended frequency range. Notice that all of these different materials have different frequency ranges at which they operate. So by picking a particular size of ferrite and knowing what frequency you want it to operate on, that allows you to pick a proper core to use as a ferrite bead. Okay, moving right along. Operating procedures. What type of station simultaneously retransmits the signal of other stations? That would be a repeater. The type of station that can automatically retransmit other stations? Well, there's a repeater, once again. There's also an auxiliary station that's kind of like a store and forward station, like connecting two other stations together. And a space station is anything above 50 kilometers in height. That's the definition of the beginning of space. So those are able to retransmit automatically. A linked repeater network, we have one of them in Oregon. I know there's one in East Texas. There's one in Arizona. These are a network of repeaters in which signals received by one are connected over a backbone and transmitted over all of them. The cool thing about that is that one station in one place can have a conversation with other people far, far, far away using the backbone and a repeater.
Is that like the East Coast reflector, Scott?
I don't know what the reflector is exactly. It's entirely possible. I know in Oregon, we've got the peak radio system, which is 50 repeaters that are all connected together. And those are connected by a combination of internet links and microwave links and VHF and UHF links that basically tie them all together. Now,
because on the East Coast reflector, when I listen to it, I can hear people in England and all the way, like way over there, Ireland.
Okay, so it's possible. I mean, we have something called the WINS system, and there are local repeaters, but then there's also internet tie-ins. So that's all part of a linked repeater system. In this particular case, it's using the internet as part of the intertie.
Oh,
so yes, we have the same thing out here. Like the peak radio system with those 50 repeaters, it also has an echo link tie-in, so people from all over the world can use it. And then they all pop up on the repeaters, and people on the repeaters can talk to people all over the world.
Oh.
So the most common repeater offset in the 2 meter band is plus or minus 600 kilohertz. In the 70 centimeter band, which is 440 megahertz, it's plus or minus 5 megahertz. CTCSS is continuous tone carrier squelch system. That's a subaudible tone that is designed when it's transmitted along with your signal to be received by repeaters. And if it's not there, if the repeater is listening for it, the repeater will not receive your signal and retransmit it. That's done to basically keep repeaters from interfering with each other. So if you can hear a repeater, but you can't access it, you could have the wrong offset. You could be basically transmitting on a frequency that it's not listening to. You could be using the wrong CTCSS tone. Again, that's, for instance, 100 hertz or 123 hertz or 156.7. And these are all published in the repeater directory along with the repeater offset. You could also be using the wrong DCS code. DCS is digital code squelch, which is a very small range frequency hopping scheme for your transmitted signal. If it doesn't hop frequencies based on what the code is telling it to, the repeater receiver says, nope, that's not one of my signals. And it doesn't copy it and it doesn't retransmit it.
When would you ever use DCS code?
DCS is used by a lot of the repeaters on the peak radio system. Like
Okay.
their main 145.13 repeater uses DCS D023.
All right.
So that's part of the repeater pack. That's part of the receiver package that they have.
Thank you.
How is the reverse function used? Reverse is used when you hit the reverse button on your handheld to listen on a repeater's input frequency as opposed to the output frequency. And why would you want to do that? Let's say that there's somebody nearby to you that the repeater can't hear, but you think that they're probably close to you. If you listen to the repeater input frequency, you might be able to hear them directly. The other thing is, that's a way to figure out if somebody is, should be strong, but the repeater can't hear them. Maybe they forgot to turn on their tone. If you can hear them, you can tell them, hey, I think you forgot to turn on your tone. What could cause your FM transmission to be distorted on voice peaks? If you over deviate, because you have this reactance modulator, if you put too much audio into it, your spectrum will spread too wide. And what's the bandwidth of an FM signal on a repeater again? See who remembers.
6,000.
FM?
6 kilohertz.
FM is 10 to 15 kilohertz.
10 to 15, okay.
So let's say that a repeater is
I was on
designed with a
mute. Dang
filter
it.
to listen to a bandwidth of 10 kilohertz wide, and your signal is this wide. What's going to happen to all this stuff here? The receiver's not going to hear it, is it?
No.
So if you are over deviating, that means that part of the signal that makes up your voice has gone away. If it's gone away and you're basically listening to a portion of you, that means that you're distorted. So you're talking too loudly, that means talk quieter or back away from the microphone. If you know another station's call sign, how do you call them? WB7MAX, N7JI, over.
N7JI, this is WB7MAX.
All right, there we go. I just called Max. He just called me. You say the other station's call, then your own. If I'm on a repeater and I say this is N7JI monitoring, that means I'm telling people, hey, just so you know, I'm here. Let's see, an amateur station that is receiving and transmitting on the same frequency, that's known as simplex. We also operate something called duplex. Notice that there's something called full duplex. Diplex is not a thing, but full duplex is what we hear when we're on our telephone, where you can actually hear and speak at the same time. That's known as full duplex. And we typically don't do that. In fact, I can only think of one situation where we could do that. You need a separate transmitter and receiver on both ends. Why do we have simplex channels in the VHF, UHF bands? And the reason being that if you are, let's say 600 feet from somebody else that you're trying to talk to, and you just want to have established communications between the two of you, you don't really need to talk to anybody else, then you can not use a repeater. A repeater is a resource that can be used by a lot of people because it can be accessed by a lot of people, typically because of where it's located. If you're just in the same local area as somebody else, then you can use a simplex frequency and not tie it up. The national simplex calling frequency, which is a frequency that everybody should get used to listening to, is 146.52 megahertz. That's kind of like, on CB, we used to call it channel 19, probably still is. That's sort of like the simplex frequency where everybody anywhere will be listening. On HF operations, CQ, 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 that means I am listening for any station. You say CQ and then give your call sign. Before calling CQ, however, you need to see, first of all, you listen to see that no one else is using the frequency, and then verify, because we have different frequency limits available based on our license class. You look to see if you're even allowed to be there and transmitting. And then you ask, is the frequency in use? The reason you ask that is because somebody might be listening to somebody else talk. You can't hear the person that they're listening to, but they're busy listening to somebody else. So you say, is the frequency in use? You might hear, yes, it is. Sorry.
Is that what we heard before when we were noodling around the bands? So one guy was calling something about frequency use?
Yeah.
Okay.
He's asking
Yeah,
if
I
the
heard that
frequency is
too.
in use. Yep. Always ask if the frequency is in use, because you never know if there might be somebody there who's just listening for someone else.
He was so busy asking that I didn't know that he had time to hear a response.
And then you call CQ. Okay, how should you respond to a station calling CQ? Here we go, Max. CQ, CQ, CQ. November 7, Juliet, India, calling CQ.
November Juliet, India, calling CQ. This is WB7MAX.
There you go. Same thing. Hey, Max, this is Scott. You just replace those with your name, with your call sign. How often do you, what's the point of making an on-air test transmission? You want to see if your transmit is working. This is N7JI testing. How do you make sure it's legal? You identify the station. This is N7JI testing. That's a test transmission. Interference is QRM. That means man-made interference. QRN is natural noise. So that's the difference between M and N. That's like lightning, static crashes. Your QTH is where you live. QSB is fading. QSY means I'm changing frequency. QSL means I confirm. QRZ means who is calling me. QRU means we're done. So this is actually a nice little short list and really represents probably virtually all of the Q signals that you'll ever need to use or ever need to understand. The ones that you need for the technician test are QRM. QRM is man-made noise. For the general exam, you add QRN, QTH, QSB. QSY means I'm changing frequency. That's on the technician exam. What is a band plan? Beyond the privileges established by the FCC. Well, we are really, really, really lucky because we are given by the FCC almost carte blanche to do anything we want. If you look at the frequencies that we have here, the different colors, with a very few exceptions, like for instance, the CW portion down here at the low end of 2 meters and 6 meters, and all this other stuff, the FCC does not tell us, for the most part, what we are allowed to do with these frequencies. They don't tell us that on the 17-meter band between 18068 and 18168, thou shalt have a channel 7, which is 18.084 and has a bandwidth of this, and you can't tune anywhere else except for the next channel up. They don't tell us any of that. The reason they don't tell us any of that is because we tend to know what we're doing. We tend to behave well, and by virtue of that, we are given the ability to literally tune anywhere between, on the 17-meter band, 18068 and 18168. The only stipulation is that our entire signal that we're transmitting falls between that lower limit and that upper limit. So the voluntary band plan is done to keep peace, to say, okay, well, yeah, this is part of the Morse code band down here. you can operate sideband down here if you really needed to. It's going to wreak some havoc, but we're trying to keep the peace. So unless you absolutely need to, follow the voluntary band plan. Now, the other part of it is that because we can tune literally anywhere in any of these bands using a knob, that's an infinite number of frequencies, right? We can go to 18110 or 111 or 1105, 1103. We can get we can have as many frequencies as we want. That also means that we are tasked with knowing, for instance, if we have 18.068 to 18.168, part of it is knowing that here are our limits. The only stipulation is what again? That all of our signal is what?
Within that.
Within that limit. That's right. Okay. So what does an upper sideband signal look like? Here's the center frequency. Upper sideband signal looks like that. How wide is an upper sideband signal?
3 megahertz.
Nope. One more. 3 what?
3 kilohertz.
3 kilohertz. This is 18068 kilohertz to 18168. Well, this right here is our dial frequency. Where would be the highest point that we could tune our radio to make sure that the entire signal stayed in band?
18165.
That's it. These are, again, part of the reasons that we have to take a test, because we are given these extraordinary privileges that just say, here's your band edges, stay inside. The test is basically saying, okay, do you understand how to stay inside? This is how to stay inside. You understand what the signals look like, how wide they are, and how to get them in band. Now, what happens if your radio has a dial, let's say it's a little bit old, and when it says you're on 18165, it's actually on 18166. Where's your signal going to be?
Outside the band.
Whose fault is that?
Yours.
That's yours. That's right. So it's important to know your own equipment and know how it's behaving. We typically don't go all the way to the edge for that very reason. Also, if it's on 18165 and it's an old analog radio, as it heats up, its frequency could drift around a little bit. So at one point you were in band, and then all of a sudden you find that you're not. So it's really important to understand where, what your responsibilities are. Okay, let's see. Again, a band plan is voluntary.
Does my radio beep at me when I'm getting to the edge of a band?
No, it beeps at you when your dial frequency is at the edge.
Oh,
now
the
you could set it up so that it beeped at you closer in, but let's say that you were on lower sideband. Well, then your limit would be different, right? Because your signal is on the other side.
Yeah, it's still the same 3K.
No, it's the other way. Because now, let's say that you're on lower sideband, and let's say that we're on 14,000 to 14,350. Right?
Okay, but I still have to stay 3 kilohertz above, so
Nope. Nope.
14
Let's say that you decide you're going to operate on lower sideband. What does lower sideband look like?
Same thing. 3
No,
kilohertz.
it's on the but it's on the other side. So
Right.
it's 3 kilohertz. So if
So
you
I
were to
gotta
put that
stay-
signal here,
I gotta be at 14,003 to stay legal.
well, and you probably, yes, but you probably wouldn't be doing that because 14,000 to 14,150 by convention, this is all CW and digital and not voice. But you also have this 150. So if you're on lower sideband, you wouldn't go below 153 because then your signal would come down to here. But that is different because this is the voluntary thing because it's inside the band. This is statutory. That is actually the law. So it's important to recognize what's what and where it comes from.
Fair enough.
Okay. When two stations show up on the same frequency, who owns it? Heard some of this on field day. Hey, you're interfering with us. Like,
You
yeah,
negotiate.
you negotiate. Yeah, nobody owns it. Public, it's a, think of it as like a space in a national park. Nobody owns it. Public service, amateur radio emergency service versus RACES. These are two very similar things. Notice the only letter that's different between these, ARES and RACES. RACES is civil. If it's civil, that means that the government is somehow involved because in civil defense. That's the only significant difference. ARES is an emergency service where you use people and ham frequencies and radios to provide emergency communication. RACES is a communication service where you provide people, ham radios, and frequencies to provide emergency services, except that this is specifically with regard to civil defense. And because of that, you register with your local government agency to do that.
What kind of agency?
It could be, well, it could be your state version of FEMA, you know, emergency response office. It could be the National Guard. It's whoever, you know, whoever is responsible for running the RACES group. Net control station. How do you, what does a net control station do? Net control runs the net. A net is short for network, which is basically a group of people who are functioning as nodes on a network that pass information back and forth to each other. So the American Radio Relay League, which is the ARRL, which is our national organization for ham radio. It's odd that it's called the American Radio Relay League, right? That doesn't make a lot of sense. Well, it turns out that the ARRL, I'll have to say, even if you don't necessarily agree with all their policies, I do recommend joining because they're the ones who largely stand up for us, stand up for our frequencies in front of Congress, and are essentially our lobbying group when the cell phone companies come and say they want to take over a band from us. They're the ones who go and fight for it and say, no, please don't do that. They do a lot of training and things like that as well. And actually somebody here found this class on the ARRL website, which is good. So anyway, the word relay is in there. Relay comes from nets, where you basically have information that's being passed from one place to another over a network. So the job of the net control station is called the net to order and direct communications between stations checking in. When you participate in a net, unless you report an emergency, you basically keep quiet to keep the frequency clear. Traffic is information passed from person to person along the net. If it's designed to, let's say, go from station A to station C, that might go from A to B to C, and here's net control right here, net control station. Well, if A cannot be heard directly by net control, A would pass the information to B passes to C, and C says, okay, I have information from station A. Here is the message. Say net control station would say, okay, well, tell station A message received. Whoop, we got a message that goes here, says received, then received, then received. Each of those stations, B and C, would basically be functioning as a relay station, connecting the net control station to far-flung station A.
Question?
Yep.
Was on a net last night, and net control was using his own personal call sign. And the last time I was on a net, they were using the call sign of the club.
Yep.
Does one make a difference over the other?
Nope.
Okay.
A net is a net is a net. Yep.
All right. Thank you.
Yep. So traffic is messages passed by stations. Good traffic handling, you receive everything you receive, you don't edit it, you just pass it along. To make sure that voice messages containing unusual words are received correctly. So I'm going to pick on Max again. Max's last name is Donor, D-O-N-E-R, not D-O-N-O-R. There might be a Max Donor, D-O-N-O-R somewhere. And if I wanted to specify in the message, this is for Max Donor. I spell Delta Oscar November Echo Romeo, taking away all ambiguity as to who I'm talking about. So any words or names that there's any ambiguity, you would use phonetics to do that. The preamble, which is basically the header of a message, is information needed to track the message. The check in a radiogram is essentially a like a telegram sent over ham radio, is the number of words or word equivalents in the text portion. So if the message was, please tell Max I am going to the zoo. Please tell Max I am going to the zoo. Okay, and your check is 9. Okay, that means there were 9 words or word equivalents in there. So if I sent it along and somebody did that and then they heard the check was 9 and they said, please tell I am going to the zoo. They said, oh, I only got 8 words. You said the check was 9. You better give it to me again. It's a way of verifying that the full message got there. Okay, so for emergencies, when do FCC rules not apply to the operation of a station? The answer is that FCC rules always apply. And here's the interesting catch-22. When can you use your ham license or equipment to operate outside of the frequency privileges of your license class, or to operate on a frequency that isn't even a ham band at all? 2 things. This will always show up. Immediate safety of human life or protection of property. There's an imminent dam burst. Your job is to get that information out, period. If you're the only way that it can be done, the cell phones aren't working or whatever, you're out of cell phone range, you want to get on a fire department's frequency and you know there's somebody there and you know how to do it, you might have some explaining to do, but if there's immediate safety of human life or protection of property, you can do anything you need to do. So you follow the rules unless the rules say you can go and not follow the rules if necessary. And that's going to show up over and over and over in this section. What amateurs can contact the International Space Station on the VHF bands? That would be anybody holding a technician or higher class license. A novice class licensee actually can't. It's very unlikely that you'll ever run into a novice class licensee. They haven't given those licenses out since the late 90s. That was actually an entry-level class that was even below the technician class license. Virtually no privileges on the VHF bands. And it's not tested for anymore. A satellite that is operating in mode UV, that's 70 centimeters uplink and 2 meter downlink. So UV, because it's UHF up and VHF down. Hey, Max, I'm sorry I'm picking on you so much.
This is good.
What mode of transmission is commonly used by amateur radio satellites? Well, we all know FM, right? FM is very common. The ISS has an FM transceiver on board. A year ago, I actually talked to an astronaut on the ISS. It was really cool. One of the highlights of my ham radio life. There are also single sideband transponders and transceivers up there, and Morse code and data transceivers as well, depending on the satellite. That can be simpler or more complicated. Some of them actually operate on HF, believe it or not. What is the impact of using excessive radiated power on a satellite uplink? Well, if it's a linear transponder and it's a wide band of frequencies, if you are wiping out the entire band, nobody else can use it. So if you're using too much power, you can block access. Which of the following is a way to determine whether your satellite uplink power is either high or is either neither too high or too low? The satellite retransmits, and you will typically be listening to yourself, listening for the satellite, listening for yourself on the downlink. If your signal on the downlink is about the same as the beacon, because a satellite is an amateur radio station, every amateur radio station has to identify itself. Very often it will be sending out Morse code. If your signal is louder than the beacon, you're probably too loud. It should be about the same strength as the beacon itself. So low Earth orbit, that is, there are 2 kinds of satellites that are up there. One are geostationary or geosynchronous. That means it's at an altitude that keeps it at the same spot with respect to a point on the ground at all times. Those are really, really hard to find spaces for, and they're really expensive to put up because they have to get about 22,000 miles up. Low Earth orbit is basically anything else that's in orbit that is going around the Earth anywhere between, you know, an hour and a half and 2 hours of orbit. They make some really weird looking paths around the Earth. But what's cool about it is that, for instance, the ISS at a height of about 220 miles goes around the Earth once every 90 minutes or so, which means that sometimes they go right overhead in the middle of the night. Sometimes they go right overhead in the middle of the day. Sometimes you don't see them for 3 days going directly overhead. So that's low Earth orbit, or LEO. A satellite beacon is information about the satellite. This is its location. This is the temperature on board. Here's the battery status. Anybody can receive this information because it's just being transmitted. So anybody with a radio who can receive the satellite information can listen to the satellite.
What frequencies are those satellites usually on?
Well, the easiest way to look is you can find them published on AMSAT. And we're going to go to AMSAT right now. So AMSAT satellite past tracker. So here's past predictions. AMSAT is the Amateur Satellite Corporation. And notice there are a lot of satellites up there right now. These are all amateur radio satellites. And so we're going to put in our grid square and use this to predict the next 10 passes. So if you want more information on this satellite, you can look at it on a map. You can also look for a listing of satellites. So here's all the stuff that's up there. Those are all amateur satellites. There's a lot of them. And let's pick one. EuconSat. Let's see if there's information. And there you go. Uplink, downlink. Here's the baud rate, 9600 BPS, or bits per second, or baud. FSK, which is frequency shift keying. And so if you want, it tells you where it is and you can listen for it.
Thank you, Scott.
Yep. There's all kinds of information on that. So in order to find just any random satellite up there, if you know approximately, if you know the Keplerian elements of the satellite, you can punch them in. And the Keplerian elements are basically from Johannes Kepler when he was working on satellites and how things orbit. Keplerian elements are values that you plug in indicating how long it's been up there, when it was launched, what angle it was launched at, what the heading is, and it will show exactly where it is at any time. So you plug in the Keplerian elements from any random satellite, and the satellite tracking program will show you where it is. Now, Doppler shift. When I made my contact with the ISS, it is important to note that if you've ever heard a fire truck go by, you know that it goes, the pitch changes as it drives by. That's because the waves are getting compressed when the thing is coming toward you and stretched when the thing is going away. Well, sound waves travel at about 300 meters per second. Fire truck, moving pretty fast, is actually it's actually moving at about 25 meters per second. That's actually pretty quick compared to 300. So it's a noticeable difference in the pitch that you're listening to. However, how fast does light travel? Everybody.
300 million meters per second.
300 million meters per second. Well, so sound would not really be affected by that. However, a satellite moving at 17,000 miles an hour actually is moving at a noticeable fraction of that. So as the satellite is coming toward you, every time it's transmitting, those waves are actually getting compressed So it sounds like it's on a higher frequency to you than it really is, which means you actually have to tune your radio slightly higher. When it's passing directly overhead, it's on the true frequency. And as it's flying away, the frequency actually appears to get lower. Now, in order to be heard by that satellite, you actually need to tune your radio the opposite way to get on the right frequency. So as it's coming toward you, you have to tune to a lower frequency. And as it's going away, you have to tune your transmitter to a higher frequency so that you get heard. That's known as Doppler shift. And it's caused by a high velocity of the satellite above the Earth's surface. Spin fading of satellite signals. Satellites rotate in order to remain stable. As they rotate, antennas might disappear from view. As they disappear from view, you can't hear them anymore. It might also be that if they're directional, the directionality might disappear for you and they might go away from view. Contesting. Contesting is an activity where you try to contact as many stations as possible in a specified period. Field day is an operating event that is not a contest, but it's still fun. It is kind of a proto contest. There are a lot of contests out there for those of us like myself who are competitive and like to do as much as possible with as little as possible, and try our skills against other people doing the same thing. So I really enjoy contesting. It's also known as radio sport.
Last night on the net, they were talking about Summer Sizzle or something like that coming up in July. Do you know what that is?
I don't. However, there's also the IARU HF World Championship in 2 weeks. I'll be participating in that one. That's an international contest.
Are
Yeah.
SOTA and POTA considered contests, or are they just ways to contact folks?
Not specifically. They're operating events.
What's the SOTA?
SOTA is summits on the air, basically mountain topping.
Oh, mountaintops. Okay.
And POTA is parks on the air, which
Yeah.
is
POTA I've heard of here in the flatlands.
Well, you
SOTA,
probably don't
no.
have much in the way of soda.
Might climb up on top of a corn silo.
I was gonna, or going on top of the Sears Tower, that or whatever it's called now, that doesn't really count. So
that would be a gas to be up there, though, wouldn't it?
yeah, wouldn't it though? To transmit from up there on 2 meters, yeah. Get on 2 meter simplex, and people from 100 miles can hear you. Okay, when operating in a contest, you send only the minimum information needed for proper identification and the contest exchange. So we don't have what's known as rag chews. Rag chew is a long, drawn out conversation between people. So Max, here we go. CQ Field Day, November, Whiskey 7, Papa X-Ray Lima. Go ahead, answer it.
Whiskey Papa X-Ray Lima. This is would I use my own call sign, or would I
just use your own call?
Okay, yeah, WB7MAX.
WB7MAX, 3 Alpha Oregon.
N7JI, 3 Alpha Washington.
Well, okay, and I'd say, well, is that Eastern Washington or Western Washington? Over.
Yeah. Eastern Washington.
Okay, thank you. This is W7 Papa X-Ray Lima Field Day. So really short exchange. It's just the information needed to complete it.
Yeah, I'm sorry I messed up on that. I wasn't.
That's okay. That's just practice.
Yeah.
Okay, a grid locator. So the entire world is split up into grid squares, which are actually rectangles. And interestingly, the rectangles are not really rectangles because the Earth is not flat, and it's not a rectangle. It's actually a sphere, but they look more or less like rectangles. They're 1 degree in latitude by 2 degrees in longitude. And in the United States, can everybody see that? Everyone see the grid square map?
Yes.
Okay.
Yes, sir.
So those are our grid squares. Each of those grid squares is a 2-letter, 2-digit number. So if you know where you live, you can figure out what grid square you're in. I happen to be in CN84. And Vic, you're in, where exactly are you?
I'm in next to Chicago in Batavia, Illinois.
So a little west of Chicago. So what? So what? Echo November 52.
Okay, we'll go with that.
Okay. Well, Actually, if you go on qrz.com, it will take your location and tell you what your grid square is too.
Okay,
So
I'll
the
do
reason
that
that
when
we
we're
use
talking.
the reason that we use grid squares is, let's just take a look at Minnesota and notice that
So
Minnesota
I'd be
has,
like an
go ahead,
EN 37.
Echo November 37. Where are you?
Yep, in Hibbing.
Hibbing. Yeah, so you'd be like Echo November 37. So the reason that we do that is because, let's look at Minnesota, for instance. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 different grid squares of which Minnesota is a part of. Or Minnesota it comprises 22 different grid squares. So let's say that I'm in Florida and you just say, well, I'm in Minnesota. Well, if you look at from Florida to Minnesota, you know, you're basically pointing in one direction. But let's say you're in, let's say you're on the North Dakota, South Dakota line where it hits Minnesota. If you're looking at EN 28, you're almost pointed due north. If you're looking at EN 13, you're almost pointed due south. And if you're looking at EN 35, you're pointed due east. If you're trying to point your antenna, right, which way do you point? If they just say, well, I'm in Minnesota. And the answer is, well, I don't know. What grid squares allow us to do is they allow us to get a little more specific as far as antenna pointing. And grid squares also allow us to be a little more specific when it comes to certain activities, like working 100 grids or something like that. Because there are certain grids where there are not a lot of people. You know, there are a lot of people in Minneapolis, but there are a lot of places in Minnesota that don't have so many people. So they make it a little more interesting as far as working all those places. Each of those grids is also then broken up into a 24 by 24 subgrid. So those are really, really tiny little grids. So I happen to know that I'm an EN84 or CN84LA, which pinpoints you down to a very small area. Radio direction finding, we also did that at our field day. We had a hidden transmitter. That's a way, and direction finding is a way that people can get used to locating the hidden transmitter, or the hidden transmitter can then be replaced with a source of noise or somebody jamming a frequency. A directional antenna can be used for a hidden transmitter hunt. And now we're into VoIP, IRLP, and stuff like that. So Internet Radio Linking Protocol is exactly what it says, internet and radio. It's a way to connect amateur radio systems through the internet using voice over internet, or VoIP. Voice over the internet is a method of delivering voice communications using digital techniques over the internet. Echolink is an application that you will install either on your phone or on your computer. You register with the Echolink folks with your call sign and you send a copy of your license, because when you transmit from your phone, you're going to be showing up on a repeater somewhere. That allows you, again, to transmit from pretty much anywhere in the world that you have an internet connection. How do you establish access to an IRLP node? Most radios will have a keypad. Everyone has probably noticed that their handheld radio that will have a keypad, 0 through 9, plus a star, plus lots of other buttons. Those are a touch tone pad. So once you've keyed your radio's push to talk button, you start pressing buttons. It'll actually send touch tones out over the air. So those touch tones can allow you to open up nodes over a repeater. A way to connect an amateur station to another station over the internet is called a gateway. And now we are into my least favorite part of this, which is rules and regs. And let me see, I think we're almost through. Yeah, we're almost through. Wow, that's cool. Okay, here we go. Rules and regs. Part 97. Part 97 is that which allows us to operate as amateurs in the first place. That is part 97 of the FCC rules. The FCC governs amateur radio. The FCC is the United States agency that governs communications within the United States. The FCC, the ARRL is a voluntary organization that works with the FCC. Basis and purpose of the amateur radio service. There are 5 things in the rules that say why we exist. One of them is advancing skills in the technical and communication phases of the art. And I recommend that everybody take a look at FCC Part 97, the very beginning, to look at the 5 reasons that we exist. I strongly recommend doing that. Definition of a beacon. A beacon is a beep, 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 beep. It's a system that basically transmits with no expectation of signals coming back to it, looking for propagation or experimental activities. That's a beacon. Here I am, here I am, here I am. A space station is anything 50 kilometers or higher above the Earth's surface. That is where space begins.
I've always wondered, since it's US based, why do they base that in kilometers?
Because it's around the world. Because by agreement, every country has space. So, you could say 30.2 miles, but it's 50 kilometers. By international convention, I think that's the height of space. When is willful interference permitted? The answer is never. You are never allowed to jam somebody, even if they're pissing you off. Which entity recommends transmit and receive channels for auxiliary and repeater stations? Those are both stations that can automatically retransmit. That would be that volunteer frequency coordinator. Who selects a frequency coordinator? That is any operator in a local or regional area whose stations are eligible to be repeater or auxiliary stations. So basically, if you have a repeater, you can vote for who is going to be the frequency coordinator. Okay, now this one, frequency in the 6-meter band, you just got to look at the 6-meter band. If you're studying for your general, this is a big part of it too, because it's just memorizing frequencies. Which frequency is in the 6-meter band? The 6-meter band is 50 to 54. Well, 52525 falls in there. 146.52, we look at the 2-meter band, 144 to 148. You just have to know that it falls in the 2-meter band right over here. On which band does a technician class operator have phone privileges? On HF. What are the limits on HF again, everybody? How many megahertz? What defines HF again? In
3 to
megahertz.
30.
3 to 30. Yep. Okay. So we're looking between 3 and 30 megahertz. And we're looking for technician voice. And we find that there's this path, there's this swath right here. On the 10-meter band, technicians can operate voice. And the answer is on the 10-meter band, right there. And it's between 28.3 and 28.5. So where can SSB phone be used in amateur bands above 50 megahertz? You look above 50 megahertz and you find SSB. And look at that. There's some there and there and there and there and there. And the answer is on every band. You can always use single sideband somewhere. Which of the following band segments are limited to CW only? Well, you got these red segments, CW only. Those are 144 and 144 to 144.1 and 50 to 50.1. And there they are. How can we use the 219 to 220 band? Well, interestingly, if you look at this band, you will see that it's right here on 1.25 meters. It starts at 222. We actually have a portion of this band that's 219 to 220 as well. It's only used for store and forward messaging systems. See this fixed digital message forwarding systems only? We have 1 megahertz that is designed just for forwarding messages. So that's kind of an oddball. Okay, why should you not set your transmit frequency to be exactly at the edge of a band or subband? Well, frequency shift, frequency drift, modulation sidebands don't go beyond the band edge. That's the big one. And to allow for calibration error in the transmitter frequency display. So all of the above. You just have to be really careful. How are US amateurs restricted in segments of bands where we are secondary? Well, you look at all these different frequencies and realize that we are not primary users of all these bands. We're primary users of a lot of bands, but this entire 70 centimeter band, we are actually secondary users to the government, which means that if the government were to say, hey, we are operating up here and you need to not interfere with us, if we hear them operating, they have primary privileges, we have secondary, we need to not interfere with them. Except for some specific restrictions, what is our maximum power limit above 30 megahertz? Well, all these bands that technicians are given access to, 1,500 watts. And considering that you can hook it up to any antenna you want, you understand why we are taking a class and you understand why you have to pass an exam to do this. The maximum peak envelope power in the HF band segments for a technician class operator, down here, that's 200 watts. And it's PEP, which is peak envelope power. Notice this PEP. And when we do some more of the general class stuff tomorrow, we're going to go into peak envelope power and how to calculate it. License classes, you are able to get a technician, a general, or an amateur extra. No, I don't know why it's called amateur extra and not just extra, but those are the three that you're able to get now. The normal term for a license is 10 years. The FCC used to send out pieces of paper that said, congratulations, here's your license. They don't do it anymore. It shows up in the FCC's database. If it's in the database, you can print out a copy of it. But if it's in the database, that's your proof that you have a license. So if it shows up in the database, you're legal. How many license grants may be held by any one person? The answer is 1. What proves that the FCC has issued you a license? If you appear in the FCC ULS database, that means you're legal. Who may select a desired call sign under the vanity call sign rules? Anybody. You just have to pay another $35. Which of the following is a valid technician class license? Well, technician class license, every US call sign begins with one of these combinations of letters. W, N, K, or AA through AL. Every American call sign begins with that. These are actually part of the international organization, part of the UN. These actually follow the same rules for prefixes as ICAO, which is for aeronautical stuff. So if you see an airplane, you can figure out where it's registered by looking at the name on the by the number on the tail. So we can have up to 2 letters in a prefix. So that would be that, and then a number, and then up to 3 afterwards. So you can have WA7OMM. You could have up to 1 and 3. You can't do 1-by-1s for personal calls, but you could have N4AXE. You could do K3TM, right? This would be known as a 1-by-2. This would be a 1-by-3, and this would be a 2-by-3. You could also do AA70K. That'd be a 2-by-2. This would be an extra class call. This would be an extra class call, and this would be a technician or a general class, and this would be a technician or a general class. So as a technician or a general, you basically have the same pool of questions, same pool of license call signs that you can get. So looking at those, we can see that which is a valid technician class call. KA1X is extra, W1XX is extra, KF1XXX would be a technician class call sign because it's 2 letters, number, 3 letters. Don't be the one who applies for the FCC for a call sign that goes like this. If your name is MJ Smith, like MJ Ott, that your call sign you want MJ7OTT. Because the FCC, I'm sure somebody will get a good laugh out of it. Why is that not a US call sign? Why can't you have it?
But you can't use the letter M.
That's right. And in fact, MJ is the prefix for England. The J makes it for the island of Jersey. So don't be that person. Grace period for an amateur license is 2 years. You don't have to, you can't operate during your grace period, but you can still say, oh, shoot, I forgot to send in my renewal. And then once it's in the database as active, you can be active again. A club, if you're applying for a club station license, has to have 4 members. Which of the following can result in revocation of a license if the FCC can't find you via email? They need to be able to get through with you via email. It also helps to have a real address too. Where can you operate from? From any, if you're on the ocean, from any craft in international waters and registered in the United States. You are technically legally allowed to operate. Now, the captain of the ship might not allow it. You need to ask permission, but if it's a US registered vessel, it's part of the United States. Which, if any, of the restrictions concerning transmissions of language that may be obscene or indecent, you are not allowed to transmit obscene and indecent. And don't get into the whole First Amendment thing. You'll end up having to fight about it, and nobody wants to do that. Manned spacecraft transmissions. NASA used to retransmit shuttle wake up stuff. Like, hey, astronauts, time to wake up, and they'd play music to wake them up. That's the only time that we're allowed to transmit music, as if we're waking up astronauts, or we are retransmitting the shuttle or ISS communications. When can you obscure a message? In other words, obscure the meaning of a message. If you're controlling a space station, you can basically encrypt it. If you're controlling a radio control craft, you can encrypt it because nobody wants any of those to crash. The ITU is the part of the United Nations, the International Telecommunications Union, that is responsible for sort of connecting all of the country's communications agencies together. So,
God, do you know what nations have notified the ITU that they don't want to talk to people in the US?
To my knowledge, nobody.
Okay.
Still. Now, I know Yemen does not allow its citizens or hams, its hams to talk with Israel.
Okay.
That's one thing. They're still technically at war. So they said if someone has a license in Yemen, they can't talk to Israelis.
Okay.
When can you receive compensation for operating a ham station? And if you happen to be an employee of a school district and you're getting paid to teach, you can use your license and get paid to be a teacher. When can you use your station to notify others of the availability of equipment for sale? Let's say you're on a swap net. You say, okay, I've got something to sell. If you're not doing it 3 times a week, and you're not like selling a bunch of stuff that has nothing to do with ham radio, then it's okay. That's the only time, because we're not allowed to make money, right? You can't make money using your ham license, at least on the air. How does the FCC define broadcasting? There's something called one-way transmissions, and there's broadcasting. They both emanate from a single location. Broadcasting is intended for the general public. One-way transmissions are for just hams. When are you allowed to use your license? For news gathering, program production, and stuff like that. There's that same thing again. Immediate safety of human life, protection of property. What type of international communications are we allowed to do? Communications incidental to the purposes of the ham service and remarks of a personal character. Well, a lot of that is, I have a doctor's appointment. I used to laugh when I used to hear people say that, people in their 50s, say, oh, I got a doctor's appointment. My sciatica is really acting up. Those are personal character things. I used to laugh. I don't laugh about it anymore because I have sciatica. And now we do talk about that. Hey, I hope the doctor's appointment goes well. I understand where it comes from. I used to be 15 years old at one point. When may an amateur station transmit without a control operator? Never. There always has to be somebody in control. Even if it's automatic, there still has to be somebody on record. So let's say that somebody transmits something to a repeater that's obscene. Who's responsible for it? It was done automatically, so it's not the person who's responsible for the repeater. It's the person who's responsible for the obscenity. The station licensee is responsible for an amateur station. The station licensee designates a control operator. When we were out at field day, the station licensee is actually me because I'm the trustee of the club. And when I say who defines the control operator is whoever is sitting down at the equipment and using the call sign. When the control operator is not the licensee, who is responsible for the proper operation, and that would be both the operator and the licensee. We already covered that, inadvertent retransmission of obscenity. That would be the originating station. And when can a technician class licensee be the control operator of a station operating an amateur extra class band segment? This happened during field day. This actually happened during field day. Somebody sat down and used his own call sign, which was a technician class call sign during field day. And we were in an extra class band. And I was standing there and I said, hey, this is N7JI, the control op for this other station, making it legal. Because we were in an extra class band segment and he had a technician class license, which did not allow him to be there. So I took over as his control operator while he was doing that.
But if he had used W7PXL, he would have been okay.
Yes, because I was standing there using, and I was the control operator for that call sign. But since he used his own call sign,
yeah,
I had to say, hey, and that comes down to who's the trustee of the station. He is the trustee of his own station. If somebody looks it up, they will see that the trustee of his station is himself, who has a technician class.
Yep.
How did that call sign get there? The call sign got there because I was the control op of his station. That actually happened during field day.
I had a very well-intentioned Elmer hang an antenna for me, and he was so excited to try out the new rig that he then fired everything up and called CQ and landed in West Virginia, and he used my call sign.
Oh, yep.
Apparently the guy in West Virginia ran me through the computer as fast as he could.
Of course.
Tried to bust me for being out of band. And I had to try and explain to my Elmer almost on the air, use your call sign.
Well, he can use yours if he says that he's the control operator for your call sign. So long as he does that, then it's okay.
Oh, he gets to be the control operator. I finally got the guy in Virginia to relax because I had an extra running my machine.
Right, but he still has to give his own call sign as the control operator.
He was trying so hard to be helpful, he used the call sign.
Yeah.
Exactly. And I was appalled that I, a mere technician, had to straighten him out on that.
Yeah, I understand that. So, all right, we are almost at the bottom. Everybody good with another couple minutes?
Sure.
Yep.
Okay. What is okay, who can transmit? Let me make sure. Okay, here we go. Who may be the control operator of a station communicating through an amateur satellite or space station? If you're allowed to transmit on the uplink frequency, it doesn't matter where the satellite puts your voice, even if it shows up somewhere that you're not expecting it. You didn't put it there, so it's legal. What? Okay, where are you going? Okay. Okay, what's an amateur station's control point? The point at which the control operator function is performed. What is remote control? That is operating a station over the internet. So that can be if I have TeamViewer or something else like that. If I am doing that, I have to be there at all times. The control operator is at the control point, and the control operator indirectly manipulates the controls. If I use TeamViewer, I'm controlling my screen. If something happens to it, the radio is supposed to turn off. That's part of remote control. Automatic control is basically the thing is happening by itself. repeater operation is a perfect part of automatic control. Okay, how often do you have to transmit your assigned call sign? At least every 10 minutes during and at the end of the communication. Notice you don't have to give your call sign at the beginning. You don't have to. Most people do, but you don't have to. Just every 10 minutes and at the end. What can transmit without identifying with a call sign? If you're transmitting signals to a model craft. If you have like a Futaba controller for controlling your remote control boat, you do not have to identify with the call sign. You just have your name, call sign, and address on the controller. You're also limited to 1 watt, although that is not one of the, below 1 watt. Specifically, it's to control model craft. What language can you use for identification in a phone subband? What does phone mean, everybody?
Voice.
Phone is voice. That's right. English. In the United States, you use English. If you're in another country, you follow their rules. How do you identify a station when you're transmitting phone signals? You can either say N7JI, or you can give Morse code. You can always use Morse code to identify. Repeaters often give a Morse code ID. It's a good idea to know Morse code so you can identify the repeater. What do the FCC rules state regarding the phonetic alphabet? It is encouraged to know and use the ITU phonetic alphabet. When using a tactical call sign, such as race headquarters, how often do you have to use your own call sign?
At the end and every 10.
At the end and every 10. That's right. So same thing. Phonetic calls or the tactical communication does not exempt you from having to use the official call sign that you have. A self-assigned indicator /QRP/MM maritime mobile. You don't have to do that, but stroke, slant, and slash are all acceptable things to add using voice. N7JI stroke 3, slant 3, /3, portable 3. Those are all valid. Third-party communications. What is a third party? Well, let's say that there's Yanni on one end and there's me on the other end, and Yanni, whose wife is not licensed yet, correct?
Correct.
She wants to tell me something. She hands him a message. He reads it to me. He's the first party. I'm the second party. She's a third party. If she gives me a message for somebody else who's in my house, she says, I have a message for Nate. Or, I can't pick Nate. For my father-in-law who lives across the street. Nate doesn't count because he has a license. But my father-in-law doesn't. He could read me the message, and I would give my father-in-law the message that says, this is from Yanni's wife. They're both third parties. In the United States and Canada, it is always legal to do that. In a lot of other countries, it is not legal to do that. And it is important to look on the list of countries with which the United States has existing third-party agreements. And last, if the FCC knocks on the door and says, we'd like to inspect your station, you have to let them in to inspect your station. Because they're looking for something. And if that something is the fact that you're interfering with air traffic control at the nearby airport, they're going to want to know how it's happening and why, and they'll basically give you a note that says you need to stop transmitting until this is fixed. So.
And there's a very nice gentleman in Vancouver, Washington, with the interference office who does that all day long.
Does he really?
That's his job.
Well, I hope he's not too terribly busy. How busy is he? Yeah. Okay, so let's cover any questions that you might have, because tomorrow we have gone through the technician thing, and tomorrow we're going to do the stuff in the general class book. If you feel like going through it, which we're going to do, notice we have already covered a lot of the stuff. That was kind of my goal. And I realize when I teach a lot of stuff anyway that goes beyond the technician. Let me make sure that I'm sharing it. Here's the general class book, and you might recognize having gone through what we did, you might recognize a lot of things in the general class book. Well, there's voltage dividers, current dividers, semiconductors. Oh, look, there's a circuit. We haven't done digital logic, but that's not that hard. Anybody recognize any of the components in this drawing?
It's a
Oh, yeah.
diode.
Yeah, diodes, capacitors. Does anyone
I
see
got
a,
the grounds.
Resistors.
does anyone see a Zener diode?
Number 5,
Number 5. How about a transformer?
Number 6.
6.
Two.
Number 2.
Number 6 is definitely
Six.
what's number
Oh,
number
number
2?
Where
Uh,
is it?
What kind of transistor is number 2?
NPN.
It's an NPN bipolar junction transistor. How about number 1? That's another kind of transistor.
It's a capacitive transistor.
That's a field effect transistor. And in particular, I believe that's a JFET, a JFET. So
Oh,
we
it's
have
JFET.
already covered a lot of the stuff for the general class. See, like there's upper and lower half power. These are the half power points of filters, ultimate rejection, insertion loss. We've mentioned that. Here's a balanced modulator. We didn't talk about that yet. Mixers, product detectors. How do you make a super het? We can cover that. A discriminator. We covered that. Frequency discriminator. We didn't do a direct digital synthesis, but we did a lot of other stuff. How about this? Anyone recognize that? Notice an amplitude modulated carrier. That's AM. I think we drew that. Here's phase modulation, frequency modulation. So intermodulation we didn't cover. Local oscillator. How does a local oscillator and RF frequency inputs? Well, there's a mixer, sum and difference, and it has a name, which is called heterodyning. Well, that's just one more word to know. There's a multiplier. We didn't do whisper, but antennas and feed lines, none of this stuff changes very much. There's a little more specifics in there. It covers front to back ratio, maximum usable frequency. Oh, look, there's NVIS. Remember we did NVIS? That's putting an antenna almost on the ground and having the signals go up into the sky. There was some backscatter. We didn't do vacuum tubes. S meter, we covered what an S meter is. So that's why I say that people that I teach, if they're really on top of it, if they never look at this stuff, typically get at least 50% on the general class exam. What gets more challenging is this right here. Notice this commission's rules. The commission's rules cover the band limits and power limits and baud rates and things like that for the high frequency bands, which general operators have access to and technician operators do not. So when we start to go back to here, like, okay, which of the following frequencies within the general class portion of the 80 meter band? Okay, so it's just a few more frequencies to learn. Region 2, frequency allocations, tower heights, things like that. So we are going to go through that stuff tomorrow. This is, and actually I normally spend 12 hours doing the technician license, and we have spent 12 hours doing the technician license. But we've also covered a lot of stuff from the general class license as well. So tomorrow we're going to be doing stuff from the general book.
You ever do anything for the extra?
I have not figured out a way to have enough time to do anything for the extra.
Do you ever do an extra specific class?
Not yet. Not that I wouldn't, I just, it's a lot of material. And I can go through and explain it, but it's
Isn't
a
it
lot of
something like
material.
1,200 questions?
No,
Or like the
no,
pool is?
it's about 600. It's a big question pool, but it's not that big. But I mean, it's really, it's all the technical stuff. It's really, really technical.
I'm assuming we are not allowed to have a band plan
Nope.
available during the test, right?
Nope, you're not.
Bummer.
All right, can we go back to this for a second?
Which,
I got the thumb,
oh, this,
pointer
the
and
right
middle.
hand rule. Yes.
right hand rule. What's the pointer in the middle?
Okay, so electric field is your thumb, magnetic field is the index finger, and this right here is the, well, oddly enough, it's called the pointing vector, which is the direction of movement of the wave. So as your wave travels this way, your electric field and your magnetic field are going to be in whatever direction the thumb and the index finger are. Now, let's see
Okay.
if you can turn it around the other way, and you'll see that one of those is now reversed because it has to be. So
Okay.
in calculus, S is equal to E cross H. If you're into vector cross products.
Thank you. I just had E, H, and S written down, and I didn't have the magnetic and pointer vector.
If you've done three-dimensional calculus and you've done vector cross products, it's S equals E cross H.
Last time I worked on that was about 20 some odd years.
Yeah, well, there's the dot product too. The dot product shows up in other places. That's a projection. So
Thank
Hey,
you.
Scott, this is a question about call signs.
yeah.
So if I went and got an extra,
Uh-huh.
would I have to give up my call sign?
No. Unless
Okay.
you want to.
I actually like my call sign.
Okay.
But then you can have people who have their extra license still using a technician
Sure.
or general
mean,
or
Sure.
technician call sign.
Sure. I mean, like I if I really wanted to, I could get a technician class call. I mean, I happen to really like my call sign because it's really nice and short. And I've had it for a lot of years, but you're KJ7 LCX, right?
KJ7 LCX.
KJ7 LCX.
Yeah.
Let's say you don't want to have the J anymore. Right? You like the suffix LCX, and you say, okay, well, I want to be K7 LCX. I want to dump something. You could look it up and see that, oh, K7 LCX was it expired in 2011. So that should be available. So if you wanted, you could keep your suffix and now shorten your call sign.
Yeah.
Stuff like that.
Okay. Yeah, I just kind of went, Dave didn't get a new call sign when he got his extra, and I thought, if people are like paying attention and saying, oh, that's a tech call sign.
Yeah, no.
He can't be okay.
And what's his call again?
He's KG7 PPA, so Kilo Golf 7 Papa Alpha.
Yeah. So I mean, he could go with like K7 PPA. Let's see if that's available. That is not. Let's see W7 PPA. Probably not. That's taken. N7 PPA. A lot of it depends on, oh, that one's available. And it's available too.
But, he just got the PPA. He should be DDH or something.
Yeah.
What website do you look at the call signers?
Well, I mean, you can look at QRZ, but the gold standard is the FCC website. So
Okay.
if anybody wants, we're going to go through and take a look at we're going to take a little tour of the FCC ULS. Because this is where your license is going to show up. So Yanni, give me something to look for. It can just be like it can be like a suffix or
N3IGT.
IGT.
Yeah.
So we're going to look up all the NIGTs. So notice I put an underscore in there. The underscore is their wild card. So we're going to look up anything that's N with an IGT afterwards to see if it's been assigned. And maybe
You want
it
to
has.
stop recording, or you want to keep this
Oh yeah,
going?
I can stop recording. Unless anybody wants me to keep recording. And let me stop share for a second and